So from the learning topics for today, or what we are trying to, or what I am trying to be covering is high performance computing cluster, concept wise, what it is, and components, what are the components of HPC, and how to submit jobs on a cluster in an interactive session or a batch job submission. An interactive, in batch job submission, we look an example of a single and array job. The software management using module system. So the way we manage, the way softwares are managed on our cluster, which is called Xanadu, is on the module system base. So I will give a brief introduction about that one. And if you're, so that when tomorrow you look at the scripts, how the softwares are sourced, because since they are software on the using the modules, these will make sense. How to monitor and control jobs, how to transfer data in and out of an HPC. So transferring data from your local machine to cluster, or from cluster to your local machine, how are you going to do it? You can do command line based, or you can have applications like we recommended, like FileZilla or CyberDuck. So any one of them you will need to transfer data in and out of cluster. If time permits, I may briefly touch on cloud computing solutions, AWS, but that's not really, that's just for the information's sake, and only if I have time. So yeah, so the first section which I will be covering today is giving you some small introduction about HPC, and talk about, initially talk about some components, and then we move into some useful commands of Linux that will help you navigate in a Linux environment. So over last 20-25 years, we have seen an exponential growth in terms of data that has been collected in different fields, and that is primarily with that has become feasible because the method or the data collection methods are much more easy, or basically easily accessible to everyone. So the data has been collected to a large scale. And such a thing is also, so similar, a boost in information or in data is also observed in genomics and bioinformatics. This large amount of data comes with two distinct problems. One is the efficient storage of data, so that you store, when you store the data, you store the data has to be stored from both the space point of view, that you're taking the least space possible, at the same time from the accessibility point, that you can access them at any point of time when they're needed for analysis. So we will not be touching that part today, but the other key thing that is associated with large data is the kind of computational resources one will need to analyze the data sets. And this is something we'll be discussing today. So using the laptop, or using a laptop, whether it's a Mac or Windows, even at the highest configuration machine, is generally suitable for building workflows or testing workflows, or testing your models. They're good enough to have a subset of your data taken on your local machine, where you can actually do work much more interactively. And you can build models, build workflows or pipelines. But once you want to launch those workflows for your full-scale data set, laptops are generally do not have an adequate resources. So then in that terms, we start looking what's the next step from laptop is. So we can look for high-end machines which have a high configuration in terms of high amount of RAM and high number of CPUs, so that we can run multiple jobs parallelly. However, scaling this one to high-end machines like desktops is not really, so the scaling is not unlimited. You are bound by the hardware that is available. So you can't keep on scaling up the desktop. So whereas the data right now is keep increasing every now and then. So what we need is much higher resources. And so what's the solution, and what can we do if the resources what we need cannot be obtained or supported by a single, you can say, desktop machine, high configuration desktop machine. So that's where the concept of high performance computing cluster comes into picture. But the whole concept is really very simple. In a simplistic term, what we are expecting is we are taking multiple these high-end desktops. So these desktops we are talking about has a RAM in an order of 250 gigabytes to going anywhere between 2 terabytes or above more than that. That's the RAMs we are talking about. And the CPUs could be anywhere from, let's say 32 to can go up to 996 or so. So that's the kind of high-end machines we are talking about. These high-end machines are interconnected so that they behave as a single unit. So that when we are trying to use those resources, we have the resources that are available are much more higher than that is provided by one single machine. So essentially, what we're looking here is, let's say we have these are the different desktops on 8 different desktops or high-end machines. They have been interconnected and they behave as a single unit. That's the basic principle of high-performance computing cluster is. And this is a picture of one of the data centers. And all you see, which are these are the machines which are lying on the side and are interconnected to behave as a single unit. And so as a user, you have an access to resources beyond what is provided by just merely one single machine. If anytime anyone has a question, please feel free to put in a chat or just unmute and ask. So I'll try to answer those ones. Now, in this section, what I want to convey is what are the key components of a computing cluster is that as a bioinformatician, you should need to know, or I should need to know, or any bioinformatician needs to know. We are not going to go really nitty-gritty details of the width, bandwidth, and switches and other things. Technical, we are not going to look into it. But the idea is like, let's say, if I'm going to go and start using a cluster, what are the components of the cluster that I need to be aware of? And so that when I'm analyzing data, I'm not making mistakes. At the same time, I'm using the resources very, very efficiently. So let's look at, so from that perspective, I'm going to explain the outline of a computing cluster. And the best way, in my opinion, to learn anything is to construct it right from the scratch. So we are going to construct a small, let's say, high performance computing cluster that may be needed by a small institute. So let's say there is an institute which the researchers came together, put some funds together. So before going to that one, so these clusters are quite expensive to establish. So generally, most of these are at an institute level. So we can expect that there will be multiple users, and the funds are, and the input is generally taken from across the researchers based on the analysis they would be doing to build these, to establish these facilities. So coming back to building the cluster. So let's say we're talking about a small research center, which is trying to build a HPC for their data analysis, and they talk across, has a conversation with people and figured out what kind of configurations they would like to have in terms of these machines. And based on that and the funds available, the center came, agreed that, okay, we are going to have 5 desktops, or you can say 5 machines. I didn't call them machines, but these are pretty much similar to desktops, except that they don't have hard drives. I will explain you why. But these are, let's say, these are the machines with the configuration of 32 CPUs and 256 gigabytes of RAM. And then the remaining 5 other machines, we thought, okay, we'll get 64 CPUs and 512 gigabytes of RAM. So depending upon what kind of jobs we are running, so let's say some of the jobs may need really huge amount of memory, so that we can run on the basic, on 64 CPUs and 512 gigabytes of RAM, and some of them may not require that compute intensive, so we can use the lower versions. Since these are the machines where all the computation and analysis happens, these are referred as compute nodes. So and technically we have 10 compute nodes in this computing cluster. Based on the properties these compute nodes share, they sometimes group together and given names. So for example, the first 5 have a similar, you can say, configuration. So they're called low mem. And the other 5 has high memory configurations, we call them high mem. They could be, but generally in clusters, they could be labeled very, very differently. They could be labeled as like vanilla, strawberry, or could be like, and different names. In our case, there are some of them are like general, and you find MCB student, then we have high mem. And so these names are very arbitrary, but what the name indicates, the names are given to a group of computer which are sharing some sort of characteristics between them. Okay. And these groups are referred as partitions and queues. The technical term of these groups are high mem is a partition. High mem and low mem are two different partitions in this compute node. Okay. So right, so we bought this 10, interconnected them well, and this whole thing is working as a single unit. So what's next? So we expect, as I said before, that these facilities are established at institute level, so we can expect n number of different users. So how do we let these users start using our facility, or basically this computing cluster? We cannot let anybody just walk in and start using clusters. There is a recipe for disasters. One is the security issue, and there will be no coordination in a usage of resources. So we need to work around that one. So in order to address those two problems, what we do is we put another machine in front of our cluster. Okay, this is the front end machine, and this particular machine is generally referred as head node, login node, or submit node. Depending from cluster to cluster, these names will change. Some cluster would call them head node, some of them would call as login node, some of them would refer them as a submit node. But the essential, what it means is this is a machine which is actually sitting in the front end of your computing cluster. How big this machine is, again, varies from cluster to cluster. Across different clusters you will be using. So in our computing cluster, these machines are very, very lightweight. These are, when I say lightweight, they don't have too much resources in terms of CPUs and RAM. They cannot support any kind of analysis. Whereas I've also seen clusters with these machines are very, very powerful, which just in case of somebody accidentally runs a program, it doesn't affect other users. But essentially, this is the front end machine, and it has two purposes associated with it. One of them is check user credentials. So every user is given a username and password. So when you're trying to log in on the cluster, this is the first machine you try and encounter. That's where you provide your usernames and password. They get verified, and once they get verified, you get the accessibility to the cluster. This machine also runs the resource management and job scheduling software. And what I mean by resource management is keeps an eye on all the compute nodes and then see, okay, how many resources are in use and how many resources are free. So based on the user request, it will look across all, it will look into the information that the user has requested, and will try to find out the resources in appropriate compute node on an appropriate partition. As I mentioned before, and it also does a job scheduling. So let's say we have 10 users and all of them want to use the resources. So who gets the priority? So generally it's first come, first served basis. So whoever submits their script or job first is the ahead of the queue, and his resources will be allocated first. There are different resource management and job scheduling software. SLURM, which is simple Linux utility and resource management. That's the most commonly nowadays. Majority of the clusters are using SLURM, but then there are other ones out there which might be using SGE and PBS. So these are different resource management and job scheduling softwares. Now, as I mentioned, these compute nodes don't have a hard drive associated with them. So this is exclusively RAM and your CPUs on these hard drives, and they have basically networks on those ones. Your data is generally stored in external storage devices. So in terms of understanding it, it's just simply like you take out your hard drive from your desktop, your laptop, and keep it outside. That's pretty much is the concept here. So your data storage, sorry, what happened? Okay. So data storage is external to these compute nodes as well as the submit node. This also since they are external, they are external. However, they're connected to all the compute nodes to all the compute nodes. So you can access your data from any of your compute nodes. The speed with which your data is read by any of the compute node is exactly the same. So it doesn't matter whether you're running your analysis on compute node 1 or compute node 10. The speed with which the data will be read and will be written out will be pretty much the same. So you don't have to prefer that, okay, I would like to use this one because this is faster. So in order to overcome that part, the data storage devices are external. And these data storage devices have your home directories, or could have your lab directories where the lab related projects are there, or very specific projects where the collaboration between labs are. Could be different ways. So this organization entirely varies from cluster to cluster. How the directories, what I mean is folders are arranged, is pretty much from the system administrator who runs the cluster. They organize it. But this is pretty much the layout of a typical HPC cluster would look like. So from a HPC point, from a bioinformatician point of view, I need to know, okay, what's the submit node is. So I have to connect to that one. So I need to know the address, what's the URL, or it's not a URL, but what's the address for that particular machine is. And there are how many different partitions are there on that, and what are the characteristics of each of these partitions is. So depending upon my job need, I should be able to figure it out, okay, which partition I would like to use. And how your data is stored on data storage devices. You can have multiple data storage devices. Because as any of the research institute grow, the data will keep on growing. So you need more and more storage devices. So these external storage devices keep getting added up to your existing cluster. So having them external, that is really helpful, because they need, as and when they need more, they keep on adding more devices, storage devices there. Any questions here with any part which doesn't make sense? Okay, so let's go to the next one. So this is the cluster which we'll be using today, or for the rest of the workshop. This is our Xanadu cluster. We have, these are the different partitions. So this is a Xeon partition with 32 you can say machines, 32 compute nodes. The number may not be exactly the same here, but just a representation. And we have an AMD partition with 22 compute nodes. Xeon reflects that the processor on these ones are Xeon processor, and these ones has the AMD processor. These are high mem ones, which have the memory the RAM is ranging from anywhere from 512 gigabytes to 2 terabytes. So any jobs which needs huge amount of memory, like transcriptome assembly, genome assembly, that's what the machines we are looking for doing it. Then we have partitions MCB student. These are primarily 2 compute nodes designated for teaching purposes. And this is for the workshops as well. So we'll be using these 2 today. Sometimes the same compute nodes could be associated with more than one partition, which is quite common. So for these 22 are associated also with Xeon and could be also referred using general partition. So the purpose behind that one is, if any particular application needs Xeon-based processors, then we can say, okay, we need a Xeon partition or AMD partition if the application is specific to AMD processors. Most of the bioinformatic applications, I would say 90% of them don't require any, there's no specificity with respect to what kind of processor they need. So then rather than looking into a smaller pool of 32 compute nodes or 22 compute nodes for our resources, if you specify general, the general is a much larger pool. So the general has a 54 compute nodes. So if you say, okay, from general, I need certain resources, then it's much easier. I think you're more likely to find resources from a pool of 54 rather than finding from 32 or 22. We have, as I mentioned, they have external data storage device. Our login node, or we refer to as submit node. So we have 3 submit nodes. They can be n. So the submit nodes are not fixed number. So as I said, I showed only one here, but they could be multiples here. The reason behind is what's the user load is. So if we have, let's say, 2,000 users at any given point of time, when we're expecting 500 users, then one machine may not be big enough to support the login process as well as the support the user connectivity. So what we do is to distribute the load, multiple submit nodes are being put in place. So we have two different submit nodes, Xanadu submit external and Xanadu submit internal. So the internal is used within our intranet, and external can be used anywhere from outside the campus. Then we have another compute node, you can say head node in place called transfer node. And this is primarily meant for transfer of data from local machine to the cluster, or cluster to local machine. The reason is that when the user is transferring transferring data, it uses certain amount of resources. And if we are doing those transfer on the submit node, it makes the submit node slow and non-responsive to user. So to avoid that one, we have a separate transfer node which are meant for to facilitate the data transfer in and out of compute node. Sometimes each of these compute node can be further split into multiple ones. That's possible. So you will see an example where we are, in our case, we have a Xanadu submit external, which we refer with a common term. But once we log in, there are 5 independent, you can say, virtual submit nodes exist, referred as HPC ext1 to ext5. We'll look into that details later, but from the understanding point of view, what we would be logging on is Xanadu submit external. So this is a pretty much simplified diagram. So we have multiple users. The users are trying to connect to the head node, and we'll use some sort of a secure connectivity and secure shell connection. That's what we use to connect it to head node. Once connected to the head node, we submit our jobs. Our jobs get queued up, and our resource manager then, based on the priority, is just going to look for the resources in our compute nodes. Once the desired compute nodes or the requested compute nodes, resources are available, the jobs are then submitted on the compute node. Why do we look for high performance computing cluster? What does it facilitate in terms of data analysis? So the thing is, it supports parallelism. So what I mean by that is it can happen at 2 different levels. So one of them is we have a really big problem. With problem is like a large data set, and we want to get a solution. One generally, you can do it by running just only on one CPU, but that's going to take really relatively long time depending upon the size of our data. What we can do is we can basically break this big problem into smaller chunks, and then each of these chunks is processed independently on separate CPUs, and we get the corresponding output. And this output is then compiled to get a final solution. So as compared to running over on one CPU, this process actually fastens the process 6 times, approximately 6 times. So we are saving a lot on time in this case. We could also have examples, which is very true for RedSeek kind of data. We have multiple files, multiple data files of the similar kind of data. So for example, we have 200, 300 different individuals being sequenced using, or we have data for RedSeek data for 200 or 300 different individuals. For each individual, we will be getting FASTQ files. So we have 200, let's say 200 each. If you're paired and we are doing, then we have 400 files. And all those 400 files actually has the similar kind of data in them. So rather than processing one file at a time, what we can do is process multiple files at the same time. So we'll be running, let's say, out of 200, we can be running 20 files at a given point of time. So it will take a shorter period of time to process all the 200. Each file can be processed again on a single CPU, or we can use the same principle of splitting the main job into smaller chunks and use multiple CPUs for each file to process. That will further you can say increase the speed of analysis and reduce the time. So essentially what we are doing is cutting down on the time and increasing the processability. This is a pictorial representation. What we're trying to achieve using a HPC cluster is we're using a decent sized machines. We are grouping them together, working as a single unit, and we're trying to make a much bigger system as compared to a single workstation or a PC. Any questions so far? Then I'll go into a little bit, just give a brief introduction about RAM and CPUs. If you have pop it in the chat or otherwise ask. Either is fine. Okay, there's no question. All right. Okay. Let's talk about RAM versus CPU. This is a very technical term you'll come across when you're trying to use computing clusters, because you have to specify resources in terms of how much RAM do you need and how many CPUs do you need. So let's look at what RAM and CPU is. So your CPU is the central processing unit where all the calculations are happening. All the mathematical calculations are actually happening. RAM is in a way where your data is, while these calculations are happening, intermittently your CPU would like to store a part of the analysis, then it actually, rather than storing on the hard drive, it actually looks for the RAM. It's a random access memory. It also loads your scripts and sometimes a part of your data, and then it sends that particular information for the CPU to compute based on that script, what the instructions are, what the data is, to let the CPU make those calculations. So the larger the RAM, the bigger size data you can address, or bigger size data we can analyze. This is a sort of like an analogy I would like to try to draw here just to explain a little bit more clearly. So if you have a problem of putting this jigsaw puzzle together to get the final solution, then if you look at, these are the 4 individuals working on the table to get this assembly done. So this, in terms of RAM, the surface area of the table is pretty much like the RAM, is analogous to the RAM. The surface area of the table will dictate what the size of the problem they can address. So if the larger the table is, much bigger puzzle can be solved. The smaller the table is, that dictates what's the size of the puzzle that they can be addressed. Now, a single puzzle can be done by individual or can be done by 4 people. When the 4 people are doing, different parts of the puzzle and they finally bring it together. So working 4 people, the whole process get enhanced 4 times. So, and you can think these people as analogous to CPUs. So that's how a problem is being addressed when you, in terms of CPU and RAM. So this is where I end up with the introduction of a cluster in terms of technical terms and what are the components as a bioinformatician we need to understand. That's the main thing I want to convey here. So the next thing what we're going to do is going to go and connect to our Xanadu cluster. And then we look at some of the properties, what the different partitions are there and how to get an information about each compute node. So let's go and look into that one. So the next part is connecting to our Xanadu cluster. So if you're using Mac and using this is your first attempt to ever trying to connect to a Xanadu cluster, or basically any kind of HPC cluster, then you will need terminal. So in order to find the terminal, go to your applications. This is for the Mac users. So you go to your applications. Inside your applications, you have utilities folder. It's pretty much at the down of all the icons that are listed. In the utilities, there is a terminal. And double click it. This will open up a window like something like that. In my case, it shows white. In your case, it may be black. Don't worry about it. That's just the coloring of it. You can customize it later point of time. So just going again from applications, in applications, go under utilities folder. In utilities, go to the terminal and invoke the terminal, which basically when double click on the terminal, it will invoke the terminal. And inside the terminal, I will show you how to connect to Xanadu cluster, but if we get to that page, that's good. And so the next, I'm going to just give a brief, I am not using a Windows, I cannot give a live demonstration how to connect to Windows, but happy to help if anybody is using Windows and having issues connecting to Xanadu cluster. I will explain how to configure Putty. If you had using any other software other than Putty, then I think you're good enough. You have good enough experience in setting up variables and connecting to the cluster. But if this is your first attempt to ever connecting using Putty, then there are a few things we need to set up. There are multiple things listed here, but I'll just go here. I think 2 key things. And after that, I think that will let you connect to the cluster. You need to provide, the first thing we want to do is to provide a host name or an IP address. So in case of the host name, what we'll be providing is our user ID. So the user ID is sent to you in the email. So it's going to be read seek user, and then there's some number. So that particular thing information is in your email, the email I have shared with you. So that's your user ID is. So you're going to put your user ID over here, and then you're going to say add xanadu-submit-ext.cam.ucSC.edu. That's what we are going to put in host name. Just repeating again. Read seek user, your number, at xanadu-submit-ext.cam.ucsc.edu is going to go in the place of host name or the IP address. Once you have put that one, I would request you to save it rather than loading it or anything else or opening it. Don't open it. Since you have put it here, so, and you don't want to keep on typing every time you come back and trying to connect. So what the best thing is to save it by some name. So give it some name to it. Under saved sessions, you can name it as RedSeek workshop, can label as Xanadu, whatever you feel like, put a name over there and simply say save. Once you say save, the name will appear in the lower panel. And here onwards, whenever you invoke Putty or when you will start Putty, you will see that name listed there. Just simply double click it. It will open a window and prompt you for the password. Okay. Okay, so this is what I would be using and to connect to Xanadu cluster. So you seek SSH command if I'm using Mac. So on a Mac, whatever the window, when you open the terminal, you have to type SSH, your user ID, which is our RedSeek user, and number at xanadu-submit-ext.cam.ucsc.edu. And that will launch you and try to establish the connection with the Xanadu submit external using your credentials. Now, please note, and this is every time we have this a little bit of confusion. So I'm going to repeat this one. So when it prompts you for the password, you will see an icon there, which is in the form of a key. In case, and what you have to do is you have to type your password. Don't expect any characters to appear on the screen or anything happening on the screen. It will appear that, okay, it's not letting you type or nothing is happening on the screen. Just keep on typing your password, finish it and hit return. If you have typed your password correctly, to let you in. If not, then it's going to give you give you another attempt at it. So give you 3 attempts and then you close the session. But that basically means you go back and I restart everything again. You restart the Putty or you start your terminal. So I'm just repeating again, when you're typing the password, it's not going to show you any activity on the screen. So no movement of the cursor, no characters appearing, as if it just froze, nothing is responding. Just please keep on typing your password and hit return, and it definitely will let you log in on the cluster. So I will just give possibly, let's say 5 minutes for everyone to get on the cluster, try their hands on to, and meanwhile, while you are trying it, I will also put my things on the screen so you can see when I'm doing it. And any one of you having any issues connecting it, put it on in the chat and we'll be able to help with that. Oh, you shouldn't be having a blank screen. So are you using a Mac or Windows? In my case, it says access denied. shouldn't be the case. So let me, if you're using Mac, just let me demonstrate what we're going to be doing. So I'm just bringing the window up, basically this material up. So okay, we are here. And let me just quickly put it on the side. And sorry, just give me a second, and I'll demonstrate it, and hopefully it will make sense. Okay, so I'm going to pull out. This is my terminal. So this is after Mac I have done. I basically open my terminal, and I'm just increasing my size of the screen so you can see it properly. All right, okay. So I'm going to SSH and read seek user 19 at Xanadu submit ext.cam.uchc.edu. That's the path. This basically is the address for the submit node. I'm a redseek user 19. That's the profile I'm using. So you use yours, and I'm going to hit return. And you need to have SSH before that. So see, it's letting me ask this particular password. So I'm just going to put the same command which I have used. If you're using Windows, Janet, can I just check basically the address is the same. So what I have typed it, you can pretty much, or whatever shared it, just remove the SSH part from there. And in the putty, just put the redseek user and your number, whatever the number is given to you, user number, and then the rest of the part there, and paste it over there, save it by a name. And I think it should be able to let you in. And if you're still having issues, I can help you out. We will be taking a break in another, maybe let's say 13 minutes. So it should be okay. Don't worry about that one. Okay, so it's prompting me for the password here. And you can see there is a key there, and I'm going to type the password red pound 0622. We all have the same password. So, and then, so there's no change in that. The key still appears. It appears like it's not letting me type, but you have to keep on typing your password, hit return. And if you typed your password, you should be able to see this big message on your screen. How many of you are not able to see this message? So you should not be seeing a blank screen, Jennifer. Oh, you're using Windows. You both are using. So let me go back to the Windows part, and maybe I'll just. So in the Windows section, under the host name or the IP address, so I would recommend just. Okay. Are you typing the pound sign properly? That's the only thing I can think of. Basically, if your pound sign is somehow different, this is my guess. Okay, I may be wrong. Sorry. I'm just trying to troubleshoot here. So just it's the pound sign has to be appropriate. That's the only thing I can think of. And the password is lowercase red pound or the hash sign followed by 06. Is it 06 or 622? Oh, I forgot now. Yeah, it's 0622. So the password is red pound 0622. That's the password you need to type. So the idea would be if you can put that address I've given in the host name, and sometimes, okay, this could be entirely institute based ones. I have seen sometimes people not able to access our cluster. If they are working from their institute's firewall somehow doesn't let you connect. That could be an issue I cannot resolve. I cannot basically help you to go around. But generally, most of the time, people are able to get in. Okay, thanks, Jennifer. Or possibly maybe either during our 5-minute break, we can look into your issue, or after the workshop, I will hang around for another 15, 20 minutes. So we can look into those ones. Janet, did you resolve your issue, or you're still having the same issue? Oh, okay, for you it's not working. And you both are using Windows, right? Okay. Maybe in the 5 minutes break, we'll just look into the issue. So for time being, I'm just quickly go through this one and just explain what. So right now it's pretty much technical, and we're not doing any exercise right now, but just, so yeah. So once you log into the system, oh, wow. Okay. Right. So once we log in onto the system, what you'll see is a message that appears up. This is generally a message put together by system administrator. So in some cases, you will not pretty much don't see anything. And sometimes you could see a significant amount of messages, as in our case. And that possibly for the system administrator to draw your attention to certain policy changes, or to take certain points in account while you're using the cluster. So that's the part is. But at the bottom part of it, you should be able to see a prompt. So the prompt is where you can actually type anything. I'm typing gibberish, but that is a problem because it doesn't recognize that. We'll look into that one. So this is referred as a command prompt. That's where we are going to type all our commands and interact with the system. So the way we interact with Linux platforms is by typing the command. We type the command, system takes the command, executes the command, and whatever output it comes, it then prints back on the screen. Okay, that's the way it is. Now, right now, what we have done is just put our username and password, and we saw the message. So what actually virtually has happened within the window, whether it's a terminal window or it's a Putty window, what you have done is you virtually has moved from your local machine to one of the submit nodes. So any command which you are going to type now is going to get executed on the submit node. So that basically means it's using the resources from the submit node. The submit node is not really that powerful, as I mentioned before. This is only meant for credential checks and running a resource manager software on those ones. So most of the system clusters will recommend, or possibly when you get an account, they will send you information that don't run jobs on a head node or the submit node or login node. Primary reason is you would be using resources from submit node and will be affecting the connectivity of other users to the cluster. Our main, you can say the powerhouse in terms of computational power is the compute nodes. So what we want is, rather than using resources from here, we would like to use the resources of the compute node. So the next exercises we'll go through is like how to navigate ourselves on the cluster to move from the submit node to one of the compute nodes with the resources what we need. Okay, this is a brief introduction again about the shell. So you have a login message. This is referred as a command prompt. On the command, you can type a command. So for example, you can say ls. ls is a command to list the contents. So it gives an empty nothing. So right now my directory is completely empty. But if I say ls-a, you'll see something it lists out. But ls is a command which lists out the contents of a directory. What are the files, folders are there. The other thing to have is to have this pound or the hash sign that basically, if it is present anywhere in most of the programming language, it indicates that anything that is following it is a comment or some sort of an information which user has put for its own reference. So for example, if I want to, I know ls-a command, I learned it and I know, okay, this is going to be a command to list items. So I can keep a reference for my list items, ls lists items. So when I hit return after this, what happens is the system will read the ls-a command and then see the pound sign. So it ignores anything that comes after that, thinking that this is something for the user reference and it has nothing to do with it. And then it executes the first command itself. If you don't have that pound sign over there, it becomes an issue, because try to interpret it as a command and tells you that, okay, it cannot do this, cannot do that, and cannot, basically there is an error in the program. It's 25 past 9, so I'll take a break, and meanwhile try to troubleshoot people who have Windows issues. So let's say 10 minutes break, so that we can appropriately troubleshoot everyone. Right. So before going that, if you, one more thing, if you want to clear your screen, so let's say there's a lot of information over there on the top, I want to clean it up and want to look at a clear screen, you can type clear and hit return. It will clean it up and give you the new on the you can sort of like a screen or fresh screen on the side. So I'll take a break now, and we will meet basically 35 past the hour, so 10 minutes from now. Okay. Troubleshooting the Windows issue. Whom would you like to, who, any one of you would like to share your screen? I will make you as a basically one of the co-hosts, so you can share your screen. So
I can share my screen if you like.
Okay. So is Jennifer?
Janet.
Janet. Okay, Janet. 1 second. Sorry.
Yeah.
Let me make you co-host. Okay, you should be able to share your screen now.
Can you see it?
Yes. Okay. Can you start your Putty?
Yes.
Okay. On the top. Okay. Wait a minute. Can you just simply say load? Select any of those ones and simply click on the load. So we'll check the address. Okay. Oh, you don't need SSH there. I'm sorry. You don't need SSH. So if you're using a Windows, you don't need SSH. SSH is only for Mac users. Okay, my mistake. Sorry. Now you can load it and then try to do, I think you should be able to. Yeah. So if you're using the Windows, you just need your user ID and at Xanadu submit. Okay, possibly type the password again. I think you maybe the password is not red pound 0622.
I wrote it.
Ouch.
Yeah, I tried it several times and it's still the same. So I just used the password from the email and you sent before, but it's not working.
So you are using 7, so I can check. Just 1 second. Let me check. And you tab. Okay. 1 second. SSH red seek user 7, right?
Yes.
No, it's letting me in. I think somehow the password you're typing some character, most likely the pound character is the issue. I would be guessing it. And it's red pound 0622. My hunch is that because otherwise it should, because I can get into your system. The password is working for you here. I've just checked your credentials and it's working. Just try the password a couple of times. Sometimes it may be. Oh, come on. It will let you about, just start again, actually. That's,
yeah.
Sorry about that. Oh, 1 second. Let's look at. Are we making any mistakes? But it's letting you. So red seek user 7. Yeah, try a password. on. Ouch. Oh, anyone who is using it and could give us suggestions, please feel free, because I can't. And it's the characters are really too small, so I'm just trying, but it's okay. Let's see, user 7. What could be?
Yeah, I was having a different issue altogether.
What was it?
Well, I've put in the host name correctly.
Uh-huh.
I didn't have the same issue. And just when I load it, it's just a blank screen. So I'm not sure if there's something interfering with connecting to the server on my end, or if anyone else is having this issue. I'm going to paste my host name in the chat just so you can confirm it's correct.
Okay. Kenneth, are you still having issues there, or you get it sorted for you?
Yeah, I'm still having problems, but I think my problems should be even simpler.
So are you using, hopefully you're not the SSH part of the whole thing is only for Mac users. So you need not to have SSH, if just in case if you're using SSH, I mean, you may not be. So what you need to do is in the host name or IP address, you have to put your user ID, start with your user ID, then add xanadu-submit-ext.cam.ucsc.edu. That's pretty much what Jennifer has. Yeah, that looks correct to me, Jennifer. I don't think there's any issue over there.
Okay, it might be on my end then. I'm on a government computer, and sometimes there are weird things surrounding
Okay.
permissions.
Yeah, sometimes I have previously had the issue people not able to access or for transfer of data, but yeah.
The issue that I'm having is that when I pull up Putty, it doesn't pull up Putty configuration. Is there a way to get into that?
No, it should show you the Putty configuration because that's how it loads. Have you, okay, again, have you loaded? So the Putty, there is a client version, there is a server version. We need to have Putty client version. I'm sure you might have Putty client version, but just in case, I'm just cross-checking that the Putty we have installed is a Putty client version.
That's my problem. I'll figure it out now. Thank you.
Okay. And for anybody else, so I think that was, I mentioned in the email, but I might not be 100% sure on that one. I said it's to have the client version. The server version is different. So because we are not, or basically when we are launching it, we are not using our computer as a server, rather than we are trying to connect to a server. So we're trying to be as a client. So check it out if you're using Putty client, Jennifer and Janet, both of you. I would recommend just to have a quick look at it. I'm sorry, guys.
Sorry, what was that last part? You said there.
So in Putty, it could be, I think the Putty has two versions. One is a client version, another is a server version. So you need to get the Putty client version. So let me, at least that's what there's some years back, or a couple of years back when I was looking, it may have changed. So let me go on my browser and then share the screen, and possibly, maybe this is a simple solution, but one second. Oh, yeah. Hopefully you can see my screen. You can, right?
Yeah, we can see it.
Okay. So if you go to download Putty, This is pretty much the first one. That's what I'll download. There's no server version. Oh, there is a server version down, but don't any good go for any of those ones. What we want is this one on the top.
Yeah, I have that. I can share my screen if that would be helpful.
Okay, 1 second. I was going to pause the rec. Right. So then, so we are on the cluster, and one of the key commands which you quite often use is just to know where we are in the system in terms of whether we are on the compute node or we are on the submit node. If you're on the submit node, which submit node we are on, and compute node, which compute node we are on. So the command is called host name, and this particular command is very useful. It tells you where we are on the system. So it says HPC ext4. So if you remember, I was mentioning something about that our external submit node or submit.external is further divided into 5 virtual submit nodes, which are starting with HPC ext1, ext2, ext3, ext4, and ext5. So right now I am on one of the virtual submit nodes, HPC ext4. So I'm still over here. I haven't migrated on the other side yet. So before doing that, I was just, now what all you can do on this one? We can do really lightweight applications like opening a file. You can do small files. You can write scripts. You can list the contents of the directory. You can create a directory. All those applications are lightweight. So you can do all those things and it will still not affect anybody else. The only thing is prohibited or basically not allowed is to do computationally intensive stuff. You have a data set, you're trying to push through some script. That's what is primarily not allowed or prohibited to do on a submit node. Okay. So before going, so we'll try to use some of the commands. So like I use the command host name here and executed it. It's getting executed on the external submit node, but this is a really lightweight, it's really not affecting anybody whosoever. We'll see some more commands. So the first command we would like to look into is to get some information about our system and cluster. So in case of SLURM, the command is sinfo. For other systems, there are equivalent commands of sinfo to give you details of that particular cluster if you are using PBS or if you are using SGE as your resource manager. And their equivalent commands are in the cheat sheet, which I was talking about before. We will look into that one later as well. So we typed sinfo, it tells you, okay, these are the different partitions with the with this particular state. So what you can see here is there are approximately 22 nodes are from general partition, which are in mixed state. Mixed basically partly the resources are in use, some resources are still available on this compute node. Allocated is the ones which everything is in use. Idle is basically nothing is in use. So these are high mem partitions. This is a Xeon partition, AMD, and this is the MCB student partition. This is the one which we'll be using for our workshop. And it has 2 compute nodes, Xanadu 68 and Xanadu 71. So each compute node also has a name assigned to it. In our case, the compute nodes are labeled as Xanadu-012, the last, whatever the number is of that particular compute node is. Then we have certain GPU compute nodes, which are primarily for processing ONT kind of data or any other application that needs GPU cores. So this is the whole detail. The only thing which is lacking here is we don't know which compute node is how many resources are available on that. What I mean by resources is how much CPUs and how much RAM is there on each compute node. So then we're going to modify this command as sinfo -n-l. So when you execute any command without anything, it has certain default display. It displays the information in a default mode. So for example, the display what you see here is a default version of sinfo command. So whenever you execute sinfo command, you're always going to see the output in this particular format. However, we can modify that display by using what in Linux terms called flags. Flags are like parameters. When you are apply, the display method changes. So we are using here two flags, -n and -l. So once you do that, you will see there's much more detailed information of the cluster is. Now what you can see is over here, you can see the compute node. You also can see the which partition it belongs to. So for example, 01 belongs to general partition and also GPU partition. As I mentioned before, compute nodes can have multiple partitions associated with them. It is idle. There are 36 CPUs on it and has 256 gigabytes of RAM on it. The ones which we will be using for the workshop are MCB students. So one of them is over here, which is 40 CPUs and approximately, I think, 370 or some 380 gigabytes on that one. Similarly, the other MCB student has the similar configuration on this one. So this is more detailed one, but here again, the problem is we are getting a big list of everything, whereas I may be interested only on information about MCB student partition, because that's what we are using in this workshop. So I'm going to use my arrow keys up and down to go to previous commands. So I'm going to, my previous command was this. This was listing all the compute nodes and their properties. Now I'm going to use a flag called -p. -p is for partition. So I want now specify, okay, give me only information about this partition. And that partition is MCB student. And now it displays only information about MCB student. So this way we can look properties of a particular compute node before asking for resources. So the reason is, let's say I want to use 270 gigabytes of RAM, and then I want to check whether Xanadu 68 or any MCB student partition compute node has that much memory or not. So yeah, it has 380, around 380 plus gigabytes of memory. So that's okay. So I can request one of these compute nodes. Okay, so hopefully that's the few commands to look at the configurations of your cluster. The next thing we are going to do is to start using resource. So if I still type the command host name, it tells me I'm still on the submit node. So I'm still pretty much lurking around on the submit node. What I want to do is to move on to the compute nodes and then start using the resources from there. And there are two ways in which we can do that. And I will demonstrate both of those ones. One is what we referred as an interactive session. So interactive session, and other one is batch job submission. In case of interactive session, you are communicating the system command by command basis. What is like you type a command, you see the output, then you type the second command and you see the output. That's similar to what I have been doing so far, like commands host name, I typed sinfo -n-l. Those are all interactive sessions. So I'm typing a command and I'm seeing the output, and then I'm typing another command. So that's an interactive way of working with the Linux system. Another is batch systems. In batch system, what you do is, let's say I have certain kind of data and I want to analyze through 10 steps. I can do an interactive session. I can do one command after the second one and so on and so forth as the output comes. That's pretty much possible. But some commands in bioinformatics could take several hours to almost like a couple of weeks and could go in months, which basically is like genome assembly or transcriptome assembly kind of processes. You don't want to wait to that job to finish. So rather than what you want to do is you want to list all those 10 commands sequentially and give the input data and then submit it to the cluster. Then what cluster does it takes your input data, take your first command, execute it, then the second command, third command, and so on and so forth. The system takes control of it completely. So that's the way of doing batch job submission. And we'll see an example of those ones also. So the first one, what we'll do is to start with an interactive session. Okay. So before starting an interactive session, we'll just execute one simple command. And I'm going to type it in the chat. If you're following along, you can do it cp-a/core. not sure the CBC is lowercase. Sorry, the one CBC there is should be a lowercase one. A1 and dash slash. So if this command, if you can execute, you'll that will be helpful. So let's say cp slash core cbc slash. All right, I'm missing dash a. Did I say dash a? It's going to take a while, and it's going to copy a directory called day1. And now we'll start. So here, one of the commands what I have used is cp. Cp is a copying command. The syntax of a copy command is cp followed by the source where you want to copy from and what the destination is. So since I'm copying a directory, I have to give a parameter says -a, which basically will copy everything, all, or what you can say, iteratively copy everything, recursively copy everything, and it says cp -a. Since it's a directory I am copying, directory is like a fancy name of a folder. I'm copying a folder from some location to another location. My day1 folder is located at this location, which is starting from root. I'll talk about root and other things in a while, but just for time being, just is good to understand, okay, this is this path where my day1 is located, and then I'm copying in my current folders. The current folder can be specified by dot. So that dot represents your current folder. So what it does, it copies day1 from some other location to my current location. We can list the contents of a directory or a folder by saying ls, by stating ls. Ls command is list. So if you say ls, is going to say, oh, there's a day1. So this is what I have copied just now. Okay. Now let's start an interactive session. So an interactive session, when we're going to start an interactive session, we have to specify, okay, we are going to go on the compute node. So we're going to, the main reason we are starting interactive session is we want to leave from submit node and want to migrate ourselves on the compute node and want to start using resources over there. So when we try to migrate to the compute node, we have to specify, okay, which partition compute node I would like to go to, and what kind of resources do I need? How many CPUs do I need? How much memory do I need? And based on that one, then the system assigns you a particular compute node based on the partition and the memory and CPU we have requested. To start an interactive session, the command is srun followed by ptty --pty. To starting a terminal, you specify a partition by -p. We have used -p flag before also. Here also -p is MCB student. Now, it so happened this -p refers to partition in both the commands, like here in srun and sinfo command, -p is for partition. But don't take it by default that in every command -p stands for partition. These things change. So you need to go back and look at the manual of the command, what the flag actually means. So I'm specifying partition is MCB student. Then I'm putting another flag saying --QoS, which is quality of services, as MCB student. I'm specifying the amount of memory I need and the number of CPUs I would need, and what's the basically name of the session. So you have to give a name to the session or the interactive session you will start. Okay, so I'm going to type here srun --pty -p mcb student, because that's the partition we want resources from, and that's what is allowed to us. Now, these flags has two different versions associated with them. One is called short version, another is a longer version. So -p can be written, partition can be specified by using simply -p flag, -p space name of the partition, or we can use the longer version of it, which is --partition. If you're using the longer version, we have to say --partition equals to MCB student without any space in either side of our equal to sign. Okay. So let me type both the commands and show you how the shorter version will look like and longer version will look like. There's no difference between whichever version you use. It's just the way they are specified. Let's say I'm going to ask 5 GB of RAM and I am DESC just one, and is the bash session. Okay, this is using, so I'm putting the pound sign right in the front. So system is ignoring it because anything after the pound is, the system thinks it's a comment by the user, even if it is a command. So, okay, so this is for the sake of demonstrating both the versions. I'm using that. So I'm going to say srun dash dash. Now I'm going to say partition equals to MCB student dash dash QoS equals to MCB student, then dash dash mem equals to 5G and bash. Okay. So two things I want to highlight here. One is we have changed the short version of the flag with the longer version of the flag. The two things are changed. Single dash is replaced by two dashes. In the longer version, we put the full name and we put equal to sign and then specify the parameter, or basically specify which partition we want to use. So MCB student. In the shorter version, you have a space. Here you have equal to sign without any space. Dash Q and dash Q dash QoS are, dash Q is the shorter version of quality of services. Dash dash QoS is longer version of quality of services. Again, same format. If it is a longer version, you have to have equal to without space and parameter specified. I'm specifying memory equals to 5G. Here I'm asking CPU as 1, but here I'm not specifying. So by default, CPU value is 1. So if you don't specify, system by default is going to give us 1 CPU. However, the default memory is 128 megabytes, which is really small and literally we can't do much around that. So we have to specify memory as 5 gigabytes. But either of these commands is going to give us a interactive session. So let's see where we are first before we start interactive session. I say host name. So I am on submit node, HPC ext4. Let me start any of the interactive sessions. I'm using this command and copy and paste here. Now the copy and pasting is a little different between Mac and Windows. In Mac, you have to Command C, Command V works. In Windows, Control C, Control V won't work because Control C is to kill a command in Linux. So you can't use Control C and Control V, but there is an easier way in Windows is you simply select it. Once you select whatever you want to copy, so let's say if I want to copy this whole thing, you just simply select it. And wherever your cursor is, basically this one prompt is, you simply do right click and the thing gets copied over there without doing anything. So it's copy and paste is done by, copy is by selection, paste is by simply right click, and it will paste the location wherever your cursor is. So I hit return. It's saying SRun job queued and waiting for resources and being allocated resources. So I have been allocated resources. Basically, I have been given an interactive session. Now, how would I know whether I am on the compute node? So the best thing is to check your status, like where I am in the system. And as I said before, hostname is the best command. And it tells me now I am Xanadu 68. Earlier I was on the submit node. Now I am Xanadu 68. So what the system has done, it has found space for me with 5 gigabytes of memory and 1 GB of space, and has moved me now virtually in that location. Now, this is a small location in which I can do the analysis, whatever I want to do. I can do all kind of silly things or meaningful things without affecting anybody else on the system. Okay, so that's the way to start an interactive session. Is essentially what I have done is, in the first time when we logged in, we moved virtually on the submit node. Now, from starting interactive session, I have virtually moved from the submit node to one of the compute nodes, and in this case Xanadu 68. In my case, I moved into Xanadu 68. It may give you to Xanadu 72, 71, doesn't matter. As long as it gives you the resources, we are interested in resources. We are not really specific about which compute node, and that's the you can see beauty of the whole system is we are interested on only on the resources to analyze data. Don't care where you get the space from on. Okay. If you have any questions, okay, should we be typing in out? Yeah, sorry, Sarah, if you can follow on, that is good. But if you think I'm going a little bit fast, then I would say just if you can type these commands, that's great. But if you can't, then I would say at a later point of time, if you can spend some time doing these exercises, will be awesome. But if right now, if you're just simply following, that's okay. All right, so just give a brief introduction about Linux. So since you have, some of us might have been the first time ever getting on a Linux cluster, and it could be intimidating because everything we are doing is using commands. That's the only negative side I can see in case of using Linux, that you're using commands rather than having clicks to move and navigate yourself. But other than, Linux is much more powerful to do a lot of things, which Windows could do same things, but has a longer route to take. But before going that, I'll just go into directory architecture, how the folders are organized. So if you have Mac, you might have a Mac drive. In that one, you may have volumes and different system folders. And then you have users. Inside users, you have admin and these basically users. If you are using Windows, you have program files. The main C drive has a program files, and then again, you have users and other things. In case of a Linux, the main drive is referred as the root, or generally technically it's called the root. And within the root, you have different directories. Similar to any other ones, they have program files or the Linux operating system files. And inside that, again, you have home, which is again the user home. And then inside that, you have user accounts. Within that, if you look between the two, the directory organization is not really very different. They're pretty much same looking. The only thing, when you're navigating between the directories or folders in Mac and Windows, you can do using clicks, which is graphical user interface. In case of Linux, this all has to be achieved using the commands. That's pretty much it. Okay. Another thing which I want to convey in case of Linux is about the instruction flow. So in case of Linux, the instructions are any program, or any, for that matter, program or a command. So let's say we use the command hostname, or we use the command sinfo. Those are commands. All these commands have a standard input, so through which they use the read the instructions in. So for example, when we are using sinfo, we specify -n flag, -l flag, and specified partition mcb student. So those are the parameters that are being read in. And then the program gets start executing using those parameters. And it has two output channels. You can say standard out and standard error. If the program or the command runs without issues, everything output comes through the standard output channel. If the program or application encounters an issue, could be our file is not formatted properly, or we did not write the program properly, or the flags we are specifying doesn't exist, and it could be an issue. In that case, it start coming through the standard error channel. By default, the standard error or standard output channels are directed to our screen, which basically means their output is directed to our screen. So when a commands get executed, output comes through standard output and gets printed on our screen. So when we typed hostname command, previously when I typed hostname, the command went executed itself successfully, and basically the result of the command hostname was an 68. So it came out as a standard output and get printed on my screen. If I the same command as well, let's say I try to rename it by something weird, let's say I add 2h in that, and it tells me that there is an issue, the command not found. So that's an error that is going to come through it. And for example, let's say host name, and I just some random flag I'm trying to put it is going to tell me that there's an issue with the command. This is basically, let's say, invalid flag -g, and it's trying to tell me, okay, what's the other? These are the only flags that are basically permissible with respect to this. So what's the use of having information separating out standard output and standard error? So we will see that when we are submitting jobs, we can collect errors separately and results separately. In some applications, if we want that, we can redirect them separately. Second very powerful thing about Linux is the use of pipes. So if you have two programs and we want to run through our data through both of them sequentially. So we input data in program 1, get the output result 1, which take that file and then feed it into program 2. So we are doing two-step process, executing this program in two time. You first executing program 1, then executing program 2. In Linux, what we can do is we can combine these two together. So what we do is we direct the standard output of program 1 into the standard input channel of second program by use of a pipe. And what happens, the data is read into program 1. It do whatever calculation it does, gives the output. The output is then used as an input in the second channel, and then we get the final output. So this way we save creating intermediate files. In Linux, these pipes are specified by using vertical lines. So you will have command before pipe and you have command after pipe. Essentially what it means is the output of first command feeds in as an input into the second command, or or in other terms, the input for command 2 comes from the command 1. And we'll see examples of those ones just for the to illustrate this further. The other thing is bow tie to syntax, not bow tie to syntax. This was mainly to put together to, if you're trying to get, if this is your first time getting yourself used to bioinformatics programs or trying to use command lines, there will be chances or instances where you would be looking into help file or syntax, which how a particular command should be used. So the help file would be written something like that, and you occasionally encounter square brackets and the values between greater than and less than signs. So I'm just trying to explain that if you look at what each of these brackets essentially means. So the main command here we are looking at is bow tie 2. Square brackets specify that anything in values inside it is completely optional. If you don't specify, the command will still execute. Then if you see anything between greater than and less than sign values specified, that basically means those values are essential. So if I'm using -x flag, in this case, I have to, and then I have to specify this BT2 index file or bow tie 2 index file. So that parameter has to be specified. If I don't specify it, my program won't run and complain of issues. So that's that's pretty much it is. And within the curly brackets, this is to indicate that these are multiple ways you can specify these parameters. So for example, bow tie 2 is one of the commands for mapping your reads to your reference genome or transcriptome or whatever you're looking at, depending upon what you're trying to achieve. You can specify forward and reverse reads. If you're paired end, if you have a single end read, you can use -u flag. And there are other formats like BAM. And finally, dash as is the same. And the same file is again optional. You can give the file name. If you don't give a file name, it's going to put the whole output is going to come on your screen. So that's how you can read a syntax of a command if you're trying to work on a new command and trying to see, okay, how can we use it? If you have any questions, please drop it into the chat. Hopefully these things are clear. If it is not, I'm happy to explain anything which is not making sense over here. So now I'm quickly go through some of the really basic commands that you will come across or you will use when you're working on the Linux system. One of them is ls, which is list the contents of the file. So you say ls and it lists day 1. One of the commands is if any of the command is out there and you want to look at the manual, or in terms of you want to look what are the different flags it can use, what are the different options you can specify. If this is a Linux command, you can use man and you can say day 1. Oh, no, sorry, man ls. So we're looking at the manual of ls command. So man ls, and it's going to tell us, okay, these are the different parameters we can specify. And each parameter is going to do some entirely different. So -a is it says do not ignore entries starting with dot. So what it primarily means is in Linux, any file or a folder starting, if the name starts with a dot, the file automatically becomes a hidden file and a hidden folder. And if you simply use the ls command, list command, it will not show you as hidden files and folders. In order to see them, we have to use -a flag, basically show everything. The other command which I end up using most commonly is -l. This is to show the info. Okay, sorry. I'm not sure how it's automatically stopped itself. I'm sorry. So -l flag is use a long list format. And you see what the difference is. I'll just quickly show it, but those are the flags I use. Another flag I use is -h flag, somewhere here. Where is that? Yeah, here. Okay, human readable formats. So rather than giving the size of the folders in bytes, this actually displays the size in terms of megabytes, kilobytes, and gigabytes. So it's easy to look at the number and immediately capture, okay, this is what the size of the file is. The last one is -t, which is to list the contents of the folder files in a chronological order. So the most recently modified file will be listed on the top of your list. So if there is a couple of files, it's okay. You can figure it out which file you are working with. But if sometimes in case of RADSEC, invariably you will have hundreds of files. And if you're modifying one file somewhere and want to see, okay, which is the most recently modified, then you can use the -t flag over there. In order to come out from this visualization of the manual, you have to hit Q for quit, or type Q for quit. It will take you out back to where we were. Okay. So this is the default ls. This is ls-a. -a will show me hidden files and folder. Oh, okay. Here. Right. So now instead of just having day A, I have other things which were hidden there. Now I'm going to say I want to use flag -l. So -l will, this is the long format version of displaying this information. It gives you some details about the permission that is associated with this directory. Day one is a directory. It starts with, if it starts with D, it's a directory. If it starts with nothing, then most likely it's a file. If it's nothing, there will be a hyphen in its place. So if there's a hyphen, most likely it's a file. If it is an L, it could be a symbolic link or something else. Then there are permissions associated with file. Who has created this particular this particular folder? That's me. I belongs to a user group called domain users. What's the size of the file? Is 1024 bytes. That's the day it was created. And that's the name of the file is. Okay. I want to see this detailed information for my hidden files also, so I can use multiple flags together. So I can say ls-l-a, or rather than mentioning them separately, I can combine them also, and that is supported in the Linux command. So you will see now both commands showing the longer version. Then 1025 bytes. I want to get a human readable format, so I'll say H, which is going to now, all rather than giving me bytes, is telling me this is 10 kilobytes in size, this is 1 KB in size. So 1 kilobytes in size. So yeah, that's the use of that one is, and other ones. Okay, so the next command which we are going to look at is creating directories. So so before doing that, I'll show you one command which comes later is navigating between directories. Okay, I'm going to clear it. ls. So this is the directory day one. So I want, since we are going to do all the activities inside day one, so I want to navigate myself or move myself from where I am right now to inside the directory called day one. So I would simply say cd day one. And that may, and now if I say ls, the contents has been changed. And if I say pwd, okay, I should have used that command. Okay. Sorry about that. I just left one command before going into this one. I'm going to do that exercise again. So if I say ls, I'm in the same previous directory wherever I was. If I say pwd, it tells me relative to root where I am actually located now, or where my day one directory is located. Relative to root, I'm inside the home directory. Inside the home directory, I am in fcam. Inside the fcam directory or folder, there is a redseq directory. Inside redseq directory, there is user 19 directory. That's my user ID. And inside that I'm located, and that has day one folder over there. Okay. Now let me. So now I'm going to so this pwd tells is the command tells you print working directory, or print it actually tells you where you are right now. So the pwd, that's the information it gave me. Now I'm going to change my directory, which is cd command, and I'm going to say cd day one, and it navigates me there ls. And if I do pwd, so there it displays. So before changing the directory, that was where I was. Now I have moved into day one directory. So there I was before. Since I moved into day one, now I'm currently into the day one directory. So anytime you have pwd, it will tell you where you are located into the system. We can create directories called with using commands mkdir. So which creates directory. Let's say we want to create a directory dir1, it will create a directory, and you can say ls. Now there is a dir1 directory that is created. So mkdir is make a directory with this particular name. We can also create nested directories, which is like, let's say I want to create dir2, then inside that I want to create dir3, and inside that I'm going to use dir4. In order to do that, I have to use a flag called -p. And what this p flag does is it verifies before creating a directory. What it means is before it creates a dir2 directory, is going to check in the folder if there is an existing dir2. If there is an existing dir2, it's not going to create that dir2, but inside that existing dir2 is going to create a dir3. And in order to create dir3 is again going to check before it creates, and so is applicable to all those particular folders. And if you say ls, you can see array, dir1, dir2, and single. That's the one. Those are the ones which were before. Now we will navigate into dir2, because just to check where the dir3 is located. So I will say cd dir2 just to check if dir3 is there. So I directed myself to dir2. Now if I say ls, yeah, there is a dir3. Let me check into dir3. So I say dir3, cd dir3, basically changing me, or where I was in dir2, it moves me into dir3. ls, there is a dir4 inside that. And if I say pwd, that's where I am right now. So I started here, basically user 19 directory, where there was a day one folder. I used cd day one, I moved into the day one folder. So my path changed, or that time the working directory was day one. After in day one, I created a basically series of directory one inside the other. So dir4 is created, dir4 is created into dir3, dir3 is created into dir2. And dir2 is created into day one folder. So now what I have done is cd dir2 basically moved into dir2. Then I can see the dir3. I can't see dir4 because dir4 is inside dir3. I navigated myself into dir3, which is directory 3, and that's where I am right now. Now I'm just going to display some quick shortcuts over here. The dot basically represents the current directory, which we, when we were copying, I mentioned about it. And double dots, 2 dots represents the parent directory. Okay. So for the dir3, the parent directory is dir2. Basically the directory in which the current directory is located is its parent directory. For dir2, day one is the parent directory. So let's say I want to go into the parent directory, which is dir2. I can simply do this one, cd dot dot, basically means take me to the parent directory of current directory. And if I do pwd, now I have moved from dir3 to dir2. I can, if I want to go back to the previous directory, before coming to dir2. So before coming to dir2, I was in dir3. So if I want to go there, I can simply say cd minus, and it takes me to dir3. If I do again cd minus, it will take me to dir2. Because before coming to dir2, I was in dir3. So the previous directory before coming to dir2 was dir3. So it took me to dir3. Now, before coming to dir3, right at this stage, the previous directory was dir2, because I came from dir to dir3. So it takes me to dir2. So using CD space dash, you can flip between two directories, which could be located very at different locations, and you want to somehow use them at the same time. So you can use the CD dash sign to flip between these directories. That's quite useful. Tilde actually represents your home directory. So you can say CD. By default, CD command's default directory is your home directory. So if you don't know where you are in the system, simply type CD and hit return. It will take you to your home directory. So if it's a PWD, it brings me to my home directory. Okay. Now let me go back before to the previous directory I was over here before coming to here. And so I can use CD dash. So it will take me to the dir3 directory. Okay. I can also specify my parent directories by double dots. So this will take me the parent directory of dir3, which is a dir2, but I want to go to day one. So what I will say, okay, take me to the parent directory of dir2. So I will use again 2 dots. So basically take me the parent of the current directory and the parent of that directory. So that's the day one, that's grandfather directory. Sorry, but yeah, essentially what I'm specifying is one directory, each double dots which jumps one directory above. And now if I say PWD, it has bring me to day one. Okay, we did CD. Okay, the last big part is actually creating writing scripts, or basically creating text files. In any operating system, there are, you can say, text editors, which help you to modify text files. For example, in case of Windows, you use Microsoft Word or text, and maybe other kind of text editors you might be having. So similarly, text editors also exist in Mac operating systems. In case of Linux, there has its own text editors, and there is a range of those ones. You might have heard of Vim, Emacs, and the other one is Nano. And so if you have been using any of those ones before, that's great. You possibly know how to use it. But if you are first time trying to get on a cluster or a Linux platform, the easiest text editor to use is Nano. So using Nano, you can actually create files, write scripts, and modify the files. I'm sorry. So I'm going to create a file called Nano. Okay. Before going into that, how do you create? So sometimes you may like to create empty files. You can create empty files by the command touch. So before doing that, let's see what all we have right now. Okay, so we have these 4 items. I want to create an empty file called myfile.txt. So the command is touch myfile.txt. What it does, it creates an empty file named myfile.txt. That's pretty much it. If anytime you want to use an empty file. You can also create files like Nano. Let's say I want to open a file and modify it. I can say Nano muffin underscore recipe.txt. I'm just putting something over there. So muffin recipe.txt, and immediately Nano opens this file over here. Okay, this is a text file. You can write anything here. The only thing is, if you want to navigate between the lines, you have to use your arrow keys, up and down arrow keys, and left and right keys to go across the line, whether you want to go towards left or right. If you go between the lines above and below, you have to use basically up and down keys. So what I'm going to do is I'm going to just copy it from here and paste it over here. So you can do that. So this is I'm just writing some items in a file. So now you can see that everything I have to edit is to go line by line. I can't click and go to between the lines. So to navigate in the file, I have to simply go one line at a time. And these files, you can type whatever you would like to. So I'm just going to create this file and just to demonstrate a few other properties. So let's say the recipe needs more butter. Don't try this recipe. I have no idea what it whether it actually creates cookies or muffins. Recipe, what else it needs? Maybe butter is good, sugar is good. High cholesterol and high sugar is not good, but okay, more. And you can, so I'm just trying to give an example to demonstrate certain things. And so I'm just filling it up so that when I close it, I would just want to use some commands to show you. Okay, this is source. Where is the sources? Sources, unknown. So I just added some lines over there. So once I have done completing what I want to write. So similarly, the way when we write a script, we will be pretty much using the same way. We will be writing line by line, whether it's our code or whether we are specifying resources and everything. We'll come to that part, how to specify resources, but just understanding that, yeah, when you be writing resources, we will literally typing into this particular file, opening this way. Once we are done with it, you can use the help commands which are listed at the bottom of it. So if I want to exit right now, so I'm using, so this caret character at the front is control. So you have to hit control and X at the same time to exit. So I'm going to hit control X. And it's asking me whether I would like to save the modified whatever changes I made. And I would say yes, because that's Y is yes. I'd say return. And then it says, do you want to keep this name or would like to modify the name? If you want to modify the name, you can go across the cursor, use your left and right arrow keys, go between the lines and okay. And I'm going to keep the same name. Now, if I say ls, I have a muffin recipe.txt, but I have no idea to know whether there's anything inside it or not. So how do we verify? One thing is just simply open it again by nano muffin recipe.txt, and yeah, that contents are there. That's great. So I hit control X. Since I have not made any changes, it will not ask me to save or anything. It brings me back to the same portal or the same terminal. There are other commands out there which are quite useful when you are using bioinformatics to look at long files. One of the command is less followed by the name of the file. Now here I'm going to, so one really useful trick in Linux, I'm not going to type the full name. So I type M and I hit tab, nothing happens. I type U and then hit tab, it automatically completes the name. What Linux has a tab auto completion function. So what it does, I say less and type M. And when I hit tab, it tried to autocomplete the name. It tried to search for the name that starts with M and try to complete it. But the problem is I have two files starting with M, myfile.txt and muffinrecipe.txt. It doesn't know which file to go for. It could be a directory name also. So anything starting with M, it is trying to pick it up. So it could not figure it out which one. So it didn't do anything. The moment I type U, now M and U together becomes, you can uniquely identify that I am actually going to refer for this file. And when this time when I hit tab, it completes the rest of the names. This is quite useful when your file names are very long. Believe me, you will see those cases, especially if you're downloading files from the web resources. Some of the files have crazy names, and you don't want to type it and make an error in overlap over a lower or uppercase or some missing hyphen, and it will not work. So tab auto completion is really useful in that scenario. So okay, I tab auto completed the name. I have less command. I hit return. It just displays the information on the screen. So this is only, let's say, some 12, 13 lines. That's okay. If this file would have been 1,000 lines, I can scroll up and down using my arrow keys or mouse and look into the contents of the file. Now to come out of here, to go back to our terminal, I'm going to hit Q for quit. So just press Q and it will bring you back. Now this is really cool. I like less more than any other ones because it doesn't mess up my screen. It's visual. I get the visualization, but at the same time, it doesn't mess up my screen. It just opens in sort of like a fresh terminal, showed me contents, and then brings me back here. Sometimes you would like to see the formatting of you don't want to use less. You just simply want to look at the format of file up and how the file looks at the start and the end. So the commands are head is followed by muffinrecipe.txt. What it does, it displays by default the first 10 lines of the command. So it just what you are seeing over here. Similarly, there is a tail command and to display the bottom 10 lines of the file in question here, muffinrecipe.txt. Sometimes your files are long. You just want to see, okay, what's the format is, and you can either you can use less to look at it, but you can also use head and tail if just you want that to be printed on the screen for reference purposes. You can have that on the screen. There's another command is cat. What it does, it just pulls out everything and prints on your screen. Not really the best. Cat is generally not used for printing out, but sometimes if you would like to, you can simply say cat and the name of the file. Everything in the file will be printed on your screen. So you have it there. All right. Okay. So one quick thing before going further is Alice. Head by default display 10 lines. You can change those number by -n. I can say -n. I say just let's say I want to see only top 2 lines. I'll say -n2 and then basically say muffin recipe.txt, and it just displays the first 2 lines. So you can you can change this number to any number whatsoever you like. If you want to get all the lines, 50,000 lines of the file, you can make it 50,000. It will print out the first 50,000 lines on the screen. We did talk about CP command, which is copying the commands. The next we talked about, going to talk about is called move command. So the similarly to CP command, a CP command is like copy, is similar to copy and paste. So you're making a copy of the file and pasting it somewhere. So copying it from a source and putting it at a destination. Similar, so that's a copy and paste. Move command is pretty much similar, is more like our cut and paste. So the file from the original location is moved. So in copy, you have an original location file and a new file is created. Whereas the move command is more like cut and paste. So the file is literally moved from the current location to a new location. Move command can also be used for renaming your files. Okay, so we will first make a copy of muffin recipe.txt. Okay, let's make a copy. So it's a CP muffin recipe.txt, and I'll make another copy. Would say let's say unknown source muffin recipe.txt. I want to save. Ignore the basically the I can say the vocabulary or the name, the words if they're misspelled. But what I'm trying to do is I'm copying a file from the source, which is actually current directory. So I'm not saying anything. It's present here right now. And I'm creating another copy, making a copy of it. And the name of the copy is unknown muffin recipe.txt. Execute it. Now just simply created the file unknown muffin recipe.txt. I can use the move command to move this file unknown. So I type U and hit tab, it auto completes. And I want to, let's say, move this file from this location to some other location. Let's say I want to move it to dir1. So I will say in the current directory, move it to dir1/. And if I say ls, there's no more unknown muffin recipe text here. Let's see if it is there inside dir1. So you can say ls dir1, basically list the contents of dir1, and it has moved over there. Move can also be used for renaming the file. So let's say this is the name muffin recipe.txt is the file. I want to rename it with a new name. So I will say move muffin recipe.txt, and let's say I just want to keep it really short, muref.txt. And now let's say ls, that name has been changed. So you can use move command to rename the files. And move actually the cut and paste kind of scenario. So it actually moves from the original location. If you change the directory, it goes to a different directory. If you're just giving a new name, it just changed the name. More than often, you will have a need to download data from cluster, download from data from internet, from web browsers. And I'm just going to show you one of the commands which you can use to download the data. So I'm going to go to this particular web page. So let's see if it takes us there. Yeah, okay. So this one brings to me to this particular location, and there are different data sets here. So people try to, when they're learning different programming languages, and try to use some data sets. Some of these data sets are being used for that purpose. Now here, what we want to do is download cars.csv data set here. Okay, so when you want to download, and I want to download the CSV file, so it looks like this is the file. So what I do is go right click, and what I'm going to copy is copy the link address. I'm not doing anything. I'm just right clicking and copying the link address. Once I have copied the link address, I come to the terminal. I use the command wget and paste what I have copied. Okay. There are other commands like curl and other things. If you're using that, that's fine. But wget you can use, and then list the file which you want to copy. Now, one thing you have to make sure when you have pasted the file name is, since we are expecting to download a file called cars.csv, our URL should end in cars.csv. If it is ending in .htm, .html, or any other kind of extensions, that basically means that's not really the correct location, and it will not download the data set. So either it may, sometimes what happens is that link is there, and you will find mostly in mostly for any genomic data sets or reference files or GTF files, they will have a link for the folder. So you have, when you click on the, so for example, if I click on this one, it will prompt me to download. That basically means this is the actual file. If it's not an actual file, if I click on this one, it will open another folder or another page listing different you can say files of different type, and you can choose one from there, whichever you need, and then paste it over there. But make sure that if your file you're expecting to download ends in .tar, .zz, or .zz, then that has to be the ending part of your URL. Once you have done that, you can hit return, and let's see here, we have now got a file called cars.csv. So let's have a quick look at this cars.csv, what it contains. Okay. We'll use the less command, because it's less messy, and so less space cars.csv, and you can see there's a lot of different observations about different cars. They have miles per gallon, cylinders, displacements, and other information, including where they're originated from. Some of them are from US, some of them are from Europe, and I think few of them are from Japan. Yeah, so there's few cars from Japan. Okay. So this is some sort of an information over here, and there are different makes like Honda, Ford is there, Mazda is there, Toyota is there, and other makes are there. So let's do some basic, you can say not analysis, I would say some understanding about this file. So first, let's count how many observations are there in this particular file. So we'll say wc-l. Which says this is a WC is a function called word count, and it count when you say -l, it counts the number of lines, and if you say cars.csv, it tells us that there are 408 lines inside it. But then, because the first two lines are our headers, so basically 406 observation corresponding to 406 cars. So, but the total number of lines in the file is 408. Okay. You can later on you can try this head, less, and tail, all those commands to actually look into the cars.csv. I will not go through that because you can use this as an exercise to do it. However, what I'm going to go for is one particular command called grep. Grep is a command which can search for certain patterns in your file. So the way to use it, grep followed by pattern space file. So specify grep and pattern. So let's say what we want to search. So we want to search, let's say, all the cars that are made in US. So that's the pattern we are searching in, and we are searching in cars.csv. Now it's going to list all the cars that are made in USV. Made in US. Sorry. So let me clear it up. Similarly, if you can also search, we can use this. We can use the same grep function to find all the cars which are Ford, make, and cars.csv. And you can see now this listed only the Ford cars here. The other cars are not listed. So you can. So that's how you can, in a file, you can look for presence of certain strings. So if it's a DNA file, if it's a DNA sequence, you can look for certain stretches. If it's a long FASTQ file, you are looking for a certain sequence, you can search for that particular sequence and figure it out how many lines do have that particular sequence. Okay, I'm going to clear up, and I'm going to show an example of a pipe right now. Okay, so let's see. So our previous command, I'm going to use my arrow keys to go back. Okay, this is command. What it did was it looked into the file and printed out all the cars which are made for which are Ford make. Now, I would like to see like how many of these cars are there which are Ford make. So if the output of this command, if I push it into WC, which is the word count, and use flag -l, then it will count how many lines are there in the output and should be able to show me how many lines are there. So I'll use a pipe separated by WC space -l. Now the output of this command, which was this whole thing, is pushed as an input in WC-L. What it does, it counts the number of lines. So the input for this command comes from output of this one. So let's see. And it tells that there are 53 lines corresponding to Fords over there. Similarly, we can also do something for, let's say, Toyota or Toyota. 26 observations. Okay. So let's say for some reason we would like to we want a file which is having only Ford and Toyota cars inside it. If we want to create a file and subset our original file, and this new file should have only the cars which are of a make from Toyota or from Ford. So how to do about that? Sorry, the first thing what we are going to do is to grab Ford and from cars.csv. So this is going to list out all the cars.csv. Now, when we execute the command, it by default, it displays on the screen because that's where the standard output is directed to. So let's redirect that output. This is a redirection arrow. And we want to redirect it to a new file. Let's say Ford _ Toyota.txt. All right. Okay, to redirect it there. And we can check by using less command Ford and yeah, it has only the Ford observations by using less command. Now in the same one, grep, and this time we are going to Toyota. And in cars.csv. Okay, so I'm using the same redirection and let's see what happens. Okay, now let's go back and look into less Ford cars. Now what the problem is, now in this file, we only have Toyota observation. The Ford observations are missing here. So what happened? All the Toyota observations, particularly Ford observations or the Ford observations were overwritten by the Toyota. That's what actually it happens. Now, let's see. Yeah, so I knew that's going to happen. So how to come around to basically how to prevent overwriting and append the file, basically add the information to the file without overwriting. So I'm going to execute the same commands which I've used, and this time I will say for Toyota file name is 2.txt. This is a new file I'm creating. Could have used the other one. So this is the first file we created, right? And this one has the same information of all the Ford cars. But this time when I'm actually going to type the Toyota cars, rather than using single arrow, I'm using double arrows. And now if I look at for Toyota 2.txt, you'll see these are Ford informations. If you go down there, the Toyota information. So this time they're not got overwritten. And the key thing to note is if you use the redirection arrow, it is whatever you're going to write now on the file, everything existing will be overwritten by the new information. If that's the purpose, what you want to do, that's great. That's no problem whatsoever. So if you, let's say if you want to replace the Ford information by just Toyota, then this using the arrow is great. But if you want to add the information to the existing file, then don't use single arrow, use double arrows. And that's basically means you're appending the file. That's what you're looking for. Hopefully that makes sense. If not, just drop a question mark in the, and I'm happy to explain that one. Sorry. Okay. The next thing I'm talking about here is creating variables in Linux. So variables is like assigning some variable, some value. So here, for example, the variable is flavor, and I'm going to say vanilla. Similarly, x equals to 2, x variable assigned value 2, and so on and so forth. We can specify different variables. We can see echo. So anytime we want to print anything in Linux, we use the command echo. Echo basically literally translate. You can say something similar to print. If you say print flavor, and we know that flavor is a variable. So if you simply say print echo flavor, it just prints flavor. The problem is because Linux has a different way of specifying a variable, that to tell system that what we want to print is not flavor word, but we want to print flavor variable. So in order to specify that flavor is a variable, you put a $sign in front of it. Anything that starts with dollar, and basically all the variables has to be specified by $ in front of them. Now this time, if we do echo flavor, $flavor, it prints the value of flavor, which is vanilla. Similarly, echo $x is going to print the value of x. When it is a $x, then it understands, okay, what we're talking about now is essentially a variable and not x on its own. All right, okay. Now this part is a little bit tricky, but I would like you to just have we will take a break. Maybe let's give me maybe another, let's say 10 minutes, and then we'll take a break. And to refresh ourselves. Okay, so quickly I'm going to, so here what I'm suggesting is, so first do ls where we are. Okay, in this one, I am saying that $ is home directory. Inside the home directory, there's a day1 folder. Go into the arrays folder. So that's what I'm going to go. So either I can see arrays here. So rather than typing the whole command, I can type cd array. If you can't see array in the current directory, you can use this command if you have copied the day1 folder. If not, then you have to go back and copy the folder day1, which we use cp/core/cbc/day1 and copied it to the current directory. Okay. ls, and in here I'm going to go cd fastq data. So these are the different FASTA files, fastq files that I have for, let's say, for around 47 different samples. And for each sample, we have a fastq file over here. Okay. You can list them. ls can list this way, or ls-1. This is one. And if you list that one, it will list one entry at a time, like this. This is an example of creating arrays. Okay. Arrays are quite useful if you're trying to submit array jobs. Array jobs is, so so just going a little back. So the batch job is like you wrote a single script, and using the script may have let's say, 5 different programs or 10 different programs or 10 different command lines through which your data is going to be analyzed. And you submit it. So the data gets, the script gets submitted, the data, or there's one data set, you read it, and then it executes. In case of, let's say, we talk about an example when we could have, especially in case of RADSeq, we could have 200 or 300 or thousands of individuals having similar kind of data. You don't want to write same script for 2000 different files. That's really not an effective way of working it out. So what we can do is we can use the same script, but we can using the same script, but we can submit all the 1,000 files using the same script, and that's called the Arrayjob submission. That's one of the ways of submitting multiple jobs in a cluster. So we're using the same script, but with our input files, every time the job gets submitted, or the scheduler submits the job, it takes different file as an input. Everything is automatically done. So by end of it, it's going to submit 1,000 jobs using the same script, but every time the input file is different. And so that way you can get over all those 1,000 files in a single command or in a single script. So, and that takes an, you can say in a way, a use of creating arrays. Arrays are being created, and then values from array are picked one by one at a time. So an array is nothing but a collection of elements. So you have 10 or 20, depending upon whatever the number of elements are. So the elements are kept one up in that particular, you can say container, or you can say in sort of in a variable, and they're separated by space. So the element 1 space, element 2 space, element 3, and we want to pick up one value at a time from there. So that's what we want to achieve. Let me show the code, and maybe that will make more sense. Okay. I'm going to create a variable called fast queue. So here what I'm doing is, let me copy from there, that's much easier. Okay. So let me dissect the command. So the inner command, if you see ls star.fastqueue, ls-1, okay, here it is ls-1. So basically listing in this particular format. After that, I'm doing star.fastqueue. Essentially, what I would do is fastqueue.gz. Okay. What I'm saying is basically list out one element at a time of the files. The star basically is a wild character, so anything can be replaced here. So I don't mind what is over here, but the file should be ending in .fastqueue.gz. So all the files have fastqueue.gz. So what it does is it lists out all the files that are ending with this particular this particular extension. Those files will be listed out. Once they are listed out, they will be saved into fast queues as an array object. Okay. Okay, maybe I'll keep on doing here so that we have reference for all those ones. Now, what I want to do is let's simply do echo. We know that fast queue is a variable, so we're going to do fast queues. Then it prints only one variable, the first one at a time. Okay. And if I do this, hopefully. All right. So one more before I go in. Okay. 0. When these fast queues becomes part, when all these items that got listed here on the top from 0 to 46 becomes a part of this array fast queue, each of these values has something called index position number. So at what position each of the file is located at. So the positioning counting in Linux starts with 0. So the first element in, if you're counting, you can start counting from 0. So this is 0 position, first position, second position, third position, and so on and so forth. The last element is at 46th position. Okay, that's how you count. You start from 0 and so on and so forth. Okay. So here, what I'm trying to say, I'm saying echo $fast queues. Since it's an array, I'm using these curly brackets, and then I'm within the square brackets, I'm specifying, give me the value located at this position, and that position is 0. That's why it prints out this particular value or this particular file name over here. But the same thing actually happened here also. Why did it do so? The reason is, if you don't specify any value over here, the default value is the 0th element. So that's why it displays the first 0th position element, which is this one. So it printed out that one. When you put an @ sign, that basically means print out everything. Don't, irrespective of the position, print out everything. That's why it printed out everything. Now, if you want to look at the what's the value or what the file is, let's say fourth position, you can simply do like that, and it will print out the position that is at the fourth location. So this is the way to pick up a one value from the element. So for example, if I set up a counter, let's say, counter is like, I start from 0, and every time I go through, every time I finish something, the counter changes by 1. It increases by 1. So now it becomes 1, then once it finishes becomes 2, and so on and so forth. So if I create such a counter and I put that counter here, and starting from 0, instead of in square brackets, let's say I put a counter here, the counter is 0. So what happens? The counter starts with 0. And since the counter value is 0, it's going to print the first one. And the moment it prints, the counter I increase by 1. So it becomes now 1. So then it's going to print the next value, then the next value, and then the next value, and so on and so forth. So every time it goes through some process, the counter increases by +1. If that happens, then we can print out all these elements one by one at a time. Does that make sense? Because that is really useful. This is really crucial to when we go to array jobs to understand. Fast queues, or basically this fast queue variable is an array. Array is like a list of items, and these items are stored based on certain index and values associated with them. So each of these element has a corresponding index number. Index number is like where in the list they are located. Since the counting is from 0, so we say the first element is the 0th element, then the first element, second element, third element, fourth element, and so on and so forth. So in order to pick up an element at any given position, we just use these square brackets and put the value inside that one. So then it prints what the element is located at that particular position. Hopefully that's clear. The next thing is, rather than giving one value, what about we keep changing? We increment this. We start with a number, but we keep incrementing that number, and so that for some reason, let's say we're incrementing by 1, so that we print out all the values. So we start with 0, and the moment it prints it, then it increments by 1. Then it prints the next one, then 0 becomes 1, 1 becomes 2, then 3, and so on and so forth. And this way we end up printing all the elements of that particular array. So, and in a way, every time we go through that, every time we go through this command, when the counter is increasing, the name of the file is different, right? If you start with 0 and we are incrementing by 1, so from 0, the next then value will become 1, and so on and so forth. So every time we'll say echo fast queues and counter. As the counter changes, the name of the file will also keep on changing every time. And we'll see how it can be used in submitting array jobs. So what I would say is just take maybe 6 minutes break. We will meet 11 o'clock. And meanwhile, anyone of you have any question, I am more than happy to answer. Some of this information may sound very basic to some people, but I think many of us possibly many of the participants are really first or new time to Linux platform. So getting everybody to the same level is really crucial for the success of the workshop. So bear with us for that if it sounds really basic. That's why we send a note in the email as well, that if you go through the material, if the material sounds you too basic, you can join us directly for the day too. But if you're here, if you have any cool tricks and all up your sleeves, more than happy to listen. All right, so I'll just pause it for okay, so let's continue from where we left. So the next part is talking about modules, especially this you would see in case of our system. So I'm going to clear this one up right now. So different systems basically have different way of what I would say having different clusters possibly have different way of providing software to the users. Some clusters do let some clusters let users to actually put to install their own applications or to install their or install their own programs. We all what we do is we provide most of the softwares, common softwares, which are extensively used by the people as a global installation, like everyone has an access to it. However, for the R and Python packages, we'll encourage users to have them installed on their own. So the way we make these packages, which are globally installed, available to the users is in the form of modules. So modules are these packages are already installed in the system, but by default, they are not available to you. Now, this is an analogy I keep on giving every time, but then it makes more sense. I think is something like if you're going to a digital library, the books are always there. All the books that are in the digital library are always there, but by default, not all, and the books don't pop up just by that and then say, okay, read me kind of. So if the book you want to read, you go and you basically go to the title and click it and it opens, and then from there onward, you can start reading it. The similar is in the case of module softwares. The softwares are there, all of them are located. But what user has to do is to add it to their environment, or you can simply, we can say, invoke it or start using it. And there are some commands around that one. So that's what I'm going to demonstrate next. So if you say module avail, that's the command to list out all the modules that are available on our cluster. So if you say module space avail, it will going to list out approximately 500 different, or maybe more than that, different programs or applications that we have on our clusters. And for the same program, we also maintain multiple, you can say, versions. So for example, this is a Trinity, which is primarily used for transcriptome assembly. And you can see there are different versions of it. So the user has the, you can say, okay, which version he or she would like to use, depending upon the analysis they're doing. If they're just reproducing an old analysis, so they're using an older package, they can invoke an older package. If they're want to use a brand new one, they can use the brand new one. So let's look at this particular package, Trinity 2.12.0. Okay. So command avail, list out all the packages. And first is, we can say module. Let me clear it, is much better that way. Clear. And if you say module list, it will tell you what modules are now available to you to use. And for right now, for me, there is no module whatsoever is available. In order to load a module, I have to use the command module load. And this time I'm going to load Trinity version 2.12.0. In the module will also be loaded if you don't specify version, but in our recommendation is to always make sure that you have a record of the version you are using in your analysis. At the same time, if you are using module system, always specify the module version number, so you have a record which version you used. Otherwise, there is an issue. It tried to load the most recent version, but the most recent version may change in every 3 or say 4 months. So the whole command changes, the whole program, the version you are using is going to change. So always have the version number over there. So I'll say module load Trinity /2.12.0, and let me check what all modules are available to me. So I'm going to use module list again, module list. Now it's going to list me all these different things, but yeah, this is what I loaded and this is what I have. Now, what are these other things over here, the 9 of them? So Trinity, in order to work, it needs other packages, other packages as well. So there are dependencies of Trinity. Trinity has certain dependencies, basically needs certain packages. It needs to be there to work. And that's what, when you write a module, we make sure these other packages get loaded along with Trinity when Trinity is called. Okay, so that's why you see these other packages, including the STSLib, SAMtools, Bowtie2, Salmon, and others. All of them are being used by Trinity. So that's why it's in there. Anytime you want to remove any particular package, you can say module RM and then give the name of the package you want to remove. So let's say module RM, and I want to remove a particular package. Let's say Salmon, this one, CV, and it removes the package, and you can use say module list. Now there is no longer Salmon got removed. You can also use module unload or RM, both will work the same way. Anytime you want to get rid of all the modules for some reason, you can say module purge, and that will take care of bringing back to where we started, like having nothing loaded. So this is the way we manage packages in the cluster. Sometimes it's required that you unload a module before you load the next module. If there are conflicts, basically conflicts of functions or conflicts of paths. In that case, we load a module, remove the module, then load the next one. But in most scenarios, in most of the cases, you possibly don't have to do it. So that's the demo for the module was. The first thing we are going to look at is a batch job submission. So we have finished and done with the interactive session. Okay, so so far what we were doing is pretty much the interactive session. We're typing a command, looking at its output, and then typing the second command, and so on and so forth. So that's an interactive way of doing, if you are doing any analysis for that matter. Now, next, what we're trying to do is a batch job submission. And batch job is nothing but you have a script or you can have instructions of instructions and commands through which you want to process your data. And you want to submit these instructions along with your input data to the cluster so that the cluster then takes care of itself, takes care of the command and start analyzing your data. And irrespective of the number of commands you have in your script, it goes through each one of them sequentially and give you the final output. Okay. So batch job or batch script consists of two parts. And so if you remember our cluster, or not a cluster, I would say our interactive session also consists of two parts. So so if anytime you want to come out of interactive session, you don't have to come out now, but I'm just want to show it. So you can type exit. Exit will take you to the host, basically submit node. So now I'm back on the submit node. I was on Xanadu 68. Now when I type exit, it brought me back to HPC ext4. One more time, if you do exit, it's going to take off the system and basically disconnect you from the server. So this is the command I used to start the interactive session, if you remember, right? So the main command was srun, but then these are the resources I am specifying. I'm specifying which partition I want to, which partition, which QoS, how much memory, how many CPUs. These are the resources I am requesting to the scheduler. When my job gets, when I execute the srun command, the whole command goes to the job scheduler and the resource manager. They look at these resources and then they find a corresponding space for me. So I have to specify even in an interactive session information about the resources. So similarly, what we end up doing is in the case of the scripts as well, we specify the resources. That becomes the first part of your script. And after the scripts, we specify the commands, and the commands are basically that's where the analysis happens. Okay, this is a simple example over here. So if you look here, this is the top part is our resource resource request. Now, just to go back to one of the quotes, or basically one of the points I made, that anything that starts with pound is a comment and the system ignores it. Yeah, that holds true in the Linux programming language. Okay, in a Linux or in the Linux operating system, if anything starts with pound, it ignores the subsequent one. So here what we have is pound and as batch. So the whole thing constitutes a single string of characters. Now this is ignored by Linux operating system. The only software that recognizes this is our resource manager. The resource manager, when it goes through this script, it doesn't look for anything else. It's only look for the lines that are starting with pound and s batch. It's only look for those lines. So the resource manager goes through the script and pick up all the lines that are pound and s batch. All these lines are picked up and then picked up corresponding variables. So -j, you can specify the name of your job, like what your job would, when you submit it, what name would you like to keep? Then you can specify parameters. How many compute nodes do you need? How many tasks you are running? So in most of the bioinformatic applications, the number of compute nodes and number of tasks are always going to be one. The only thing that varies is the CPUs, which is -C flag. So it picks up, okay, how many CPUs the user is requesting. It picks up which partition user want to go to, what's the QoS is specifying, what is the memory he's requesting. And it also, you can also get email notifications when your job gets submitted, when your job encounters an error, or when your job finished. So the as batch --mail -user, you can put your email ID. And so the emails IDs that are supported are Gmail and Yukon domain. So if you don't have Yukon domain, you can use Gmail. And then you can specify when you want to receive the notification. And then finally, what you have is there are two channels. I specify standard error and standard error. So rather than those channels printing on anywhere else, we specify print them out in these two different files, .out file and .error file. The %J here, what we see here, is getting replaced by the job ID number. So anytime cluster submits a job, basically anytime scheduler submits a job ID is given. So when you submit this job, your output file name will be myscript-job ID number.out or job ID number.r, looking at error file or an output file. Okay. So to demonstrate this example, let's me quickly, I don't want to, I can start. Okay, I'll start an interactive session again. Okay. So I am on right now, start an interactive session again. I'm in Zanardo 68. Okay. Alice, let's see where I am on day one. So I'm going to go into day one, Alice, and this time I'm going to go into single. There's a directory called single. So I'm going to go into single. And S. So if you are following along and don't know where I have navigated myself, so I'm going to type it into the chat. It's a CD tilde space day one / single. That's where I am. Right? Oh, sorry, single has a double A. It doesn't have a double A. It's a single E. So that's a typo over there, please. Okay. Now here, what I have is 3 different files or folders, whatever you see here. You can basically see that this is a FASTQ file. So quite clear. And we'll look into what are FASTQ files tomorrow. But then I have a file called fastq.sh. Now this is a script file. So it's always a good idea to put an extension, basically being and consistent into the extensions you put for the files you create. And especially for the script. So if your shell scripts are there, I always have my shell scripts labeled as .sh, R scripts as .r, and Python scripts .py. So if you don't have an extension, let's say here, fastqc.sh, simply fastqc, the program will run. If you submit the job, cluster will take care of it, because Linux doesn't care about extensions. This is the good thing about Linux is, so one good thing is, like if you have a text file, CSV file, TSV file, any file, as long as it's a human readable, Linux less command will open and show you what's there inside. You don't need an Excel to open a CSV file and Microsoft Word to open a document file. So that's the good part of it. So that basically means it doesn't care about extensions. So if you simply create a file called fastqc and have all our scripts inside it and submit, the program will run, no doubt about it. But 3 months down the lane, if you come back and look into this directory, it will be very difficult for you to make it out actually which one of them it was actually a script. You just simply see fastqc and you will be thinking, okay, whether it's a script, it's a job, or what it is. There are only 3 files, but as you keep on going deeper and deeper into bioinformatic analysis, folders may have many number of files, and having an extension will make your life much more easier. Okay, so fastqc.sh is our shell script. So I'm going to open it. We can open it using nano, or we can open it using less. It doesn't matter. So I'm going to just simply use less and open fastqc.sh. Okay, so this is our resource header. Now, some parameters, resources are mandatory to specify. Some resources are optional. Okay, not everything. So for example, when you start an interactive session, we only specify partition, QoS, memory, and CPU. That's the 4 parameters. We didn't specify emails and other things because those are optional. You don't have to give it. If you want it, you can get the information. Similarly, we didn't specify dash n, dash uppercase n, lowercase n, or the number of CPU, a number of compute nodes, and the number of tasks, because those are optional and have a default value of 1. Going here. So we have resource header. We specified job name is fastqc. So we have a fastq file. We are going to do a quality check of that particular file. Sorry, 1 second. I typed the thing, but I think in a direct message. So let me type to everyone. That's the one. Okay. So job name, and then have number of tasks is 1, number of CPUs I want to use is 2. So what I want to do is, if you remember our, okay, let me put, I think I have a slide for that one. That's awesome. Okay, this is what we're doing here. Okay. We have a fastq file. What we're going to do is split into 2 chunks, and each one of them is going to run into parallel CPUs, and then we get solution, and this comes out, we'll get the compiled solution over here. Okay, this side and the script on this side and that side is exactly the same. Okay, so I'll go on this side, it's much better. Since we are needing 2 CPUs, we are running in parallel. We are asking for 2 CPUs. CPUs per task, we have asked for 2. Memory, we have asked for 2 gigabytes. Partition is MCB student. That's what we are allowed to use. And QoS is also MCB student. %x is replaced by your job name. So basically all the %x will be replaced by fastqc, and %a will be replaced by the job ID number. So %j or %a both will replace the job ID number. So you essentially output files will be fastqc underscore job ID number dot out, fastqc underscore job ID dot out. Those are 2 files that will be created. I'm sorry. And we are specifying partitions and memory and everything. So since these are starting with pound s batch, Linux is going to ignore it, but because the script is first going to go to the resource manager or job scheduler, it's going to read all the lines that starts with s batch and pick up all the information from here. Based on it's going to create some space for us and then submit the script. Once basically push this script to the compute node where it has found the resources. Once it pushed to the compute node is not working on resource manager. It has a Linux operating system and Linux programming. So what it does is, then it ignores everything which is starting with pound. It's a clever way of doing it. So now the compute node is ignoring it. It only looks for the actual commands which are not starting with pound. And if first command it executes is host name, and then date, and date when the program start, date when it ends, so you can get an idea how long it takes. Now, why do I have a host name over here? Primarily due to reason that sometimes our applications is likely to fail. Could be bad coding from our part, or could be some issue with the system. If we believe that the issue is with the system and we want to get to the system administrator telling, okay, we are facing an issue, and this is the compute node I was running my job on. And then it's much easy for system administrator to pretty much focus on a very specific compute node and look and what the actual issue is. If I run a job, it fails, and I believe it's a compute node, and I don't have a host name idea, I don't know where it has run. And if I drop an email saying the system administrator, okay, my job was running on the cluster, but it failed, and I have no idea which compute node. System administrator is not going to go through 80 compute nodes to troubleshoot the issue. He's just not. He's going to ask you to resubmit the job, get the information on the compute node if possible, and then if you face the error, he's going to troubleshoot it. So that's why we have the host name. So just get an idea where the job was running. Then we are loading our software, fastqc. Again, module load fastqc. So you need to have a fastqc application. We are saying make directory, creating a directory fastqc out. That's where our output is going to go. And this is the syntax to use the fastqc command. So we say fastqc -t is the number of threads. These are called threads. How many parallel processes we are running? 2. So number of threads are 2. We are running 2 processes. So always match this value with this value. So the number of threads you're asking in the command should be same as the number of threads you're requesting from the resource manager. They should always be matching. Then you are specifying where our output has to go. And this is our input file. That's the syntax of FastQC. So there's not much of a change here. So if you look at FastQC manual, this is how the command is specified. But hopefully the rest of the things make sense, that -t is to run in two parallel, basically two threads of this command. I'm going to hit Q. Now we want to submit this script. So the command to submit the script is as-batch. So you say as-batch, and then you say the name of the script, fastqc.sh. I'm going to hit return, and then I'm immediately type a command and explain what that is. Okay. So I submitted the script saying as-batch fastqc.sh. And the moment the job gets submitted, it says submitted batch job, and this is your job ID number. So all the %A's here will get replaced by this job ID number. And %X will be FastQC. So you will have FastQC underscore 458.645.6435.out and .r. So then you have, for that particular job run, you have a separate error and out file. So if you rerun this script for some reason again, the error and out file will change because your job ID will change. So for every run, you will have a separate job ID, a separate error and out file. And in this way, if you want to see some issue has happened at submission, you can look into, okay, what you have submitted at what time and what was the issue, if you want to trace back some error that way. SQ is a command to check the status of a job. What's the status of the job I just submitted? It doesn't mean that I submitted the job will start running. Sometimes it doesn't. Sometimes resources are not available. So your job goes into pending state. It's looking for the resources. Fortunately, mine is running. So this is the FastQC job we submitted. It's running. And it was when I did SQ command, at that time it was running for 2 seconds. There's another one which I'm running, which says it's running for 9 minutes. And the name of the command is bash. This bash is the interactive session I've started. So the SLURM also take account, or basically keep a record of the interactive sessions a user starts. So everything you submit to the resource manager, it keeps an account of it. So it tells you that, okay, this is your, it tells me it's in my interactive session, and this is the script which I have submitted. Okay. It tells me the job ID number, which partition I have asked for, was the name of the job is. That name is going to appear over here, right? That's the name I was using, and that name is using here. And this is a user ID number. It's not complete. That's okay. What's the status is? It's running. How long it is running? What's the complete node it is running on? It's Xanadu 68. Okay. Now, if I go back and do SQ, this job is no longer listed, because that has finished. Once the job has finished, it is no longer listed there. And my interactive job is still running because I am in there. So it's still listed there. Now, if I say ls, you will see this FastQC and the job ID number .out and FastQC job ID number .error. It's always a good idea to look into that one if there are any issues with the program running. So main thing we are looking in these ones is words like error or something like that. So there is no error. This is the progress report of the job. So that is particularly done. Yeah, it is okay to submit your script on the head node. You can submit your scripts on from the compute node. You can submit your scripts from the head node. That's fine. There is no issue whatsoever with that. Sorry, I forgot to mention that. So I am in an interactive session, so I'm submitting from there. But if you are, let's say if you already written the script and you don't want to start an interactive session, you just take that script and then submit it. And you can submit the job from the head node or the login node. You don't have to start an interactive session for that. All right, and then the output goes into FastQC the output goes into .out folder. That's the folder over there. I'm not going to go into that one, but it's always that when your command finishes, check your .out and .error file. So it has that there. That's where it Xanadu 68 it was running. That's a host name, a command output. That's the date, and that's the date at the end, start and end. So you can get an idea like how long it was running for. There's one very, very critical command, and I won't say critical, but crucial command. If I don't have an idea about like how many resources to specify, or what kind of resources I should be giving, whether what I'm asking for is too much or too less, I use a command called SF. SF followed by the job ID number, and the job ID number is this. Okay. So I say SF 4586452, and what it does, it provides me efficiency of the resources. So let's look at the efficiency. So CPU utilization is 62%. Yes, Thomas, that's correct. So if one of the programs that is not available as modules, then and you know how to install in your local home directory, and in your system it is a permissible, then you can give paths. That's particularly fine. So you set up the path variable in those cases. I'm sorry. So as the CPU utilization is 62%, that's fairly okay. Now looks at the memory. So the memory is, the memory I asked is 2 gigabytes. Of that, 1.28 MB is only used. So only 0.6%. That's like, I'm oversubscribing the resources. But since I'm asking only 2 gigabytes in that system level, 2 gigabytes is nobody's going to bother, or even to 5 or 10 gigabytes, nobody's going to bother you. Or say you that you're doing oversubscription. But think about, like, if you're asking 100 gigabytes and you're using 0.06%, people are going to be really annoyed, because you are just asking too much resources and not using them adequately. So it's always a good idea to have some idea about like how much to ask for. Oversubscription is like hogging the resources, whereas you're not using them. Same is with CPUs. If you write a command, generally if you write a Python script or an R script, those are by default are going to run on one CPU, unless you have used specific libraries for multi-threading. But most users, when they write Python and R script, they're always going to run on one CPU. You can ask 10 CPUs, but still your program is going to run on one. 9 of the CPUs are just sitting idle doing nothing. So that's like oversubscription of resources. There's no need to ask even 2, because it's going to run still on one. The other one is not going to do. It's not like, okay, if this fails, it's going to switch to that one. No, it's not going to switch. It just simply give you an error and break down the whole, basically give you an error and stop the program. So there is no advantage of specifying more resources. So this was the single job submission. Let's look at the more funnier part, which is array, and maybe a little bit more complex. And hopefully I'll try my best to explain that it makes sense. Okay. All right. So in the previous command, previous script, what we submitted one script and we have one input file, and that worked fine. But typically in RADSIC, you will have a scenario more like an array job. You have multiple samples, like from here, I have, for example, 47 different files. I want to submit all of them, but I don't want to write a script for each one of them. That basically means I have to write 47 files, or I have to write one line for each of the files. And then I'm doing serial analysis. Then I am not taking the advantage of cluster. So what we do is, in this case, we submit the array, we submit the job in what is referred as an array mode, or it's also called Arrayjob Submission. So everything else is same, nothing else changes. Your resource manager is particularly exactly the same what we have seen before. However, we are specifying how many array jobs are we running. So I'm saying that I want to run 47 array jobs. Actually, that's the wrong number, because I have, including 0, I want to run only 46. So from 0 to 46. So this value is wrong. We'll correct it. So I want to submit 47, let's say, including 0, total 47 jobs. And each job, when I say job submission, means I want to submit the script 47 times. And every time the script gets submitted, the input file should be a different one. If we can do that, then that's the greatest thing we can do, like use single script and use all our files and run one single command, and all the files get submitted without doing anything. Okay. So when the array job runs, so the array job has to keep a track of, okay, how many jobs it has submitted. So when it submits a job, it creates a variable to keep track of how many jobs are submitted. And that variable, or you can say counter, to keep track of how many job it is submitted, is called SLURM array task ID. So when the first job it submits, the value is 0. And the second, when you submit the one more job, the value becomes 1. Then one more 2, then 3, and so it keeps incrementing by 1. Okay. So when the first time this job is, so let's say we wrote this script. I'll go through the script. So let's say when I submit this script, immediately this job will be get submitted. The first time the SLURM array task ID will be 0. And when the second time the script gets submitted, it becomes 1, 2, and so on and so forth. So every time the when script gets submitted, the SLURM array task ID is different. The number is different, starting from 0, increasing up to 47 or 46 or 47. Okay, hopefully that makes sense. Then module load fast QC. And if you remember this variable over here, it's pretty much exactly the same variable. What if you remember when I was talking about creating array variables, it's the same fastq array variable with have all these file names listed in series and basically one after the other. Okay, so think about this whole thing. Think about this whole thing as this list over here. The first element is 0, second element is 1, 2, 3, and so on and so forth. And when I say input file, I am saying input file from array, pick up the element from the array fast QCs, and the element you are going to pick up is corresponding to the value of SLURM array task ID. Just repeating again, my input file, the file which I'm going to analyze, is being picked up from the array variable fast queues, or from array fast queues from here. And from fast queues, using the square bracket I'm specifying, pick up the element number that corresponds to SLURM array task ID. Hopefully that makes sense. Now let's go back and what happened. So let's say the script I submitted the script the first time the script gets submitted. So the SLURM array task ID is 0. So this it creates this whole big variable, and in variable, what we are saying in fast QCs and fast queues, pick up the 0th, because this value is 0, pick up the 0th element. So it picks up this element over here. It submits the script, then comes back and submit next script. The moment it submits the next script, the counter increases by 1. Now the value of SLURM array task ID is 1. So now we are saying, okay, from fast queue arrays, pick up we submitted a 0th element, pick up 1th element, so 0 and 1. So it pick up this time when you submit to the next file. Submit it, so the SLURM array task ID again increases by 1, so it becomes 2. Now here we are saying that from fast queue array pick up the SLURM array task ID, which is 2, second element, so first element, second 0th element, first element, and second element. So this is the second file. So every time it increases, and every time the input file keep on changing. So with the same script, we are able to submit all those files in a single go. Anybody who didn't get it or it's still not clear, please just say one more time explanation, and I'm happy to go through this. But if it is clear, that's great. That's awesome. Because this is how the SLURM array task IDs work. Any questions anyone is having? Just let me know. I'm happy to go through this one. Otherwise, hopefully the whole concept is every time you're submitting a script, a new input file is being used. Okay, because that's the input. Okay, let me go again. So there's a request to just review again. So so hopefully you remember when we create this variable, when we say fast queues, and then we say ls-1. So basically -1 will list only one item in a line, and then we specified, okay, what are we listing? So here we simply listing from basically this directory star.fastq file. So all the fastq files will be listed like this over here. Okay? So let's say the output of this command is nothing but this one, and this one, and in an array format. So fastqs is an array that will hold all these values. In FASTQ array, these are all elements. This is 0th element. This is first element. The counting is from 0. So this is 0th element. This is first element, second element, third element, then fourth element, and so on and so forth. So those are how the elements are. So if I simply say, okay, give me the fourth element, then you'll say 0, first, second, 0, first, second, third, and fourth. So this is the fourth element. So that's the ways, that's what it means. Now, when we are submitting the script, the resource header or everything remains the same. The only thing we are telling here is submit arrays from 0 to 47. And there is %8 afterwards. Okay, so the %8, which I forgot to mention, is to tell the system that any given time, run only 8 jobs actively. Other jobs can wait, but any given time, no more than 8 jobs should be running. And now why we do it? So if I have 2,000 jobs, I don't want to, if I submit 2,000 jobs and all my jobs start taking space on the cluster, then people will get sometimes annoyed and possibly would complain, okay, you are taking up all the resources. So to be just considerate, you say, okay, I want to submit 2,000 jobs, but at any given time, 200 jobs should be running, no more than that. So when those, when any job from the 200 gets finished, then the new job comes in. Yeah, so file names, these file names can be anything. They don't have to have 0011122, because anytime you create this ls1, the order will pretty much retain the same. So it will pick up according to that one. I have 000102 like that. If you have that, that's great. But if you don't have that, that's not end of the world. You can still use the pretty much the, so the one of the questions is, do we need to have this 000102 in the file names? No, you don't have to. If you, let's say if these are your sample ID numbers or sample names, so in case of sample names, these values could be entirely different. They may not even have a zero digits to specify which one it is. But in that case, yeah, you have to be a little bit clever in that way, the way you are going to pick those ones up. You'll see the case when we're running array jobs tomorrow. But yeah, but yeah, it doesn't have to be incremental in that way. So that's the question. Okay, so that's the thing is like I'm running only 8 jobs at any given time. Okay, so anytime, so when I submit the script, because I'm submitting multiple jobs, so the SLURM, who's a resource manager, want to keep a track of how many jobs have I submitted. So it keeps a track by something called SLURM array task ID variable. Creates a variable called SLURM array task ID. And what it does, it keeps the it remembers the ID of the task, which task it has submitted. So the first task, when it submits, its ID is 0. So the value of SLURM array task ID is 0. When it's finished submitting 1 and submit again the same script for the second file, then this changes to 1. It increments by 1 every time it submits the file, and keeps on submitting until it reaches this value over here. The number of SLURM arrays it's going to submit is the number value over here, the higher value over there. So when it submits the first time, it takes the script, let's say it takes the script and then submit it, because it's the first job, it starts counting from 0. So the ID is 0. So the whole value of SLURM array task ID is 0. Okay, let's keep that in mind. And we create this array variable. This array variable hold the name of all these files here. Okay. Now from this array variable, we are going, that's okay, we created this one. Now what we are saying is, okay, this is a way of, now here what we are doing is simply choosing a file from this array and assigning it to input file variable. Okay, this is meant to choose a file from here, from our big list. And the way we are choosing is from this array, we are choosing the file based on the SLURM array task ID number. So when the first time we are submitting, the ID number is 0. So from the array, FASTQ's array, you pick up the 0th ID number. The 0th ID number is this file. So basically your input file is this file over here. And when you're running fastqc, you say fastqc-t2, 2 threads, output, and you say your $input file. $input file get replaced by this input file, which is basically this file over here. Once it finished submitting it, because it's keeping a track of it, it increases its value by 1. So now the SLURM array task ID, which was 0, becomes 1. it does the whole this operation again. And in this one, now it counts one because this value is one. From the fast queues array, it want to pick up the 1th element. So this is 0th element. This is 1th element. So this is the input file now. Second time when it is submitting, this is the input file. Similarly, when it submits again, third try when submit one more time, the ID number changes to 2. So this value is 2. So we are saying from fast queues, pick up the 2nd element. So this is 0th element. This is the 1st element. This is the 2nd element. That becomes our input file, and that gets submitted, and so on and so forth. Every time the ID changes, every time new file is being picked up and used as an input. And this keep on changing until SLURM array task ID becomes equal to this number, which is 47. Once it goes to 47, it stops submitting any more jobs. Okay. So let me quickly clear this up. I'm going to go back up and go into the directory called array. Okay. And let's look at what's there in FastQ data file, FastQ data folder. Okay, these are our FastQ data folder. The names are a little bit different. Here is FastQ, here it is fastq.zz, so it doesn't matter. That's okay. Now let's have a look at our script. So this time I'm going to open using Nano, and it's located into FastQ data directory. So the data is located into FastQ data directory. So I'm going to open using Nano, Nano FastQ array.sh. Okay, open here. What I'm going to change here is, one thing I'm going to change is this is 646. Because that's the number of, starting from 0, this is the 46th job I would be submitting. So the total file number is 47, but since we are counting from 0, you end up in that 46. Okay, everything is fine, except here that the file extensions, because here it was .fastq, right now we have .fastq.zz, so we have to put that properly so that it picks up those files. Otherwise, it's not going to pick up anything because none of the files end in .fastq. They end in .fastq.zz. So the full that way it's not going to pick up. So in order to pick that one up, we have to specify really proper suffix. Okay, the rest of the code is exactly the same. So I'm going to just come out of here, Control X. Yes, I want to save it to the same file. Yes. Now I'm going to do the same thing as batch and submit the file fastq array.sh. And quickly, I'm going to do SQ again to check the status. And now if you can see, and I'll run again one time. Okay, one more time so that I can explain these things. So, okay, when I submitted the batch job, my job name is 4586477. And these are actually my SLURM array task ID. So here is my SLURM array task ID is 0. When it was 0, it picked up 0th element from this list, which was this file. When my SLURM array task ID was 1, it picked up the first element from this array, which was this list, and it just picked up this one. When it was 2, it picked up this one. When it was 3, it picked up the next one, so on and so forth. Now, any given time, I'm running only 8 jobs, right? And because I did %8, so these are the 8 jobs are running. The rest are waiting. Once any of them is finished, the next job comes in. So here, if you see, one of the jobs get finished. So then none of the one of the jobs gets finished. Which one gets submitted? I think the 0th job got finished. So last one was 7. The 8th one came in. Here, basically, most of the previous jobs are finished. So now these jobs are running. But any given time, there are only 8 jobs that are running, or I am using resources corresponding to 8 jobs at any given time. And that's pretty much it is. And if you look at it, okay, if you do SQ, I think it has finished. Yeah, the jobs are finished, but they're pretty quick. For each of the jobs, you will get, each job will get error and out file separately. Okay, this is for the 0th one. This is for the first one. And it's a good idea to check all of them afterwards. This is pretty much where my okay, it's my effort with respect to explaining how to submit jobs and in terms of whether it's a interactive job or it's a bad job or it's an array jobs. That's what I wanted to cover, and that's pretty much done. Any questions anywhere anyone has, I'm more than happy to answer. Okay, so there's one question, definitely Thomas pointed out that you can submit jobs not only on this interactive session, you can submit the jobs from the submit node also. You don't have to be in an interactive session to submit a job. Any questions other than that? And I would be, otherwise I'm going to move to the next files. And these are pretty much presentation files. So I will just cover, make them a little bit. No questions. That's good. Hopefully it's clear. Either it's really super confusing or it's a super clear. Hopefully the later. Oh no, clear. Yeah, yeah, later. All right. So this is the cheat sheet. This is the cheat sheet I was talking about. So the Xanadu works using SLURM, or the works on the SLURM resource manager. So other systems we may work in like PBS, LSF, SGE, load leveler, any one of those ones. So when you start having that, then your Linux commands won't change. They will remain the same. But the way you specify resources to the scripts and use the resource manager commands, for example, sbatch, squeue, srun, these are all commands for the resource manager. These are not Linux commands. So these commands are going to vary between different platforms, or can say different resource managers. So for example, so yeah, if anytime you want to cancel a job, let's say you submitted a job and you want to just immediately want to cancel it, you can say cancel space the job ID number. Just give the job ID number after. So just quickly check squeue. Squeue will give you, okay, which jobs you are running, and then you say cancel space the job ID number and cancel the job. The corresponding cancel is QDEL in PBS, and SGE is QStat, QDEL actually in that one also. And similarly, for all of the, most of the variables which I have talked about have that corresponding values in all of those ones. So you can come back and depending when you're using your own cluster and you're looking for equivalent parameters, this is the cheat sheet you can use as a reference. Okay, factors to be considered before resource request. The main thing to understand is, or to identify, is what the program you're using is trying to do. Is it trying to do processes which are more memory intensive, or is going to do, is performing more on processes? It's more process intensive. If your job is more memory intensive, you need really good amount of memories. Sometimes the jobs are both memory intensive and needs good amount of CPUs also. So examples are like genome assemblies and transcriptome assemblies. These are really heavy memory intensive jobs. At the same time, they also need good amount of CPUs to run it. The processes like read mapping, read trimming, fast QC, all those processes are process intensive. They not need really huge amount of memory, small amount of memory, and they could be able to do it. So have an idea about that. And based on that, you ask for resources. Other thing is the multi-threading enabled in the application. So as I mentioned before, like people write R and Python script and think, okay, I asking 4 CPUs, make it 4 times faster. No, even the publicly available softwares have to be written in a particular using certain codes and packages to make it run in parallel, to basically break your original data into chunks and process simultaneously. In most cases, if you look at the manual of an application, you will see options like threads or CPUs or in parallels. So those are basically means that you can run job in parallel. If they don't specify like use of threads or parallel, it is not enabled for parallel, don't ask for more CPUs. It's just not helping in any way. If you're not sure, there are can go out, look at the reference manuals. Sometimes they have some reference manuals have a very good benchmarking with them, which specify that how much file you, what's the size of the file, and how much CPUs and how much RAM would you be needing. But not all of them are have that kind of information available or provided. So in that case, you possibly have to go to blogs and discussion threads. So biostar.org is one. Sequencers is another one. If you want to get some help from us, we're more than happy to help you out, to give you some suggestions what you need to be using. So email us at cbcsupport@ucon.edu. We have certain cluster etiquettes, which we try to project every time, is to do not run code on the submit node. That's the primary one. Do not SSH directly into that node. This is like you bypassing this. There is a way you can bypass the submit node and can directly connect to compute node. You can directly go to the compute node bypassing the submit node. That's possible. But that's discouraged in a way, because if you bypass the submit node and bypass the resource manager, then the system doesn't know that you are running some job on compute node or some resources are in use. System still thinks, okay, those resources are free. So that's a little tricky. Other thing is, do not submit jobs, a large number of jobs without testing. So it's always a good idea to test your job into small script and make a small test data set and run your script. If it runs fine, then go for the larger data set. It is okay if you are okay. This is okay maybe for shorter jobs if you don't do testing and then submit. But jobs like assemblies is a big no, because if your job fails after 3 weeks, you're losing a time of 3 weeks to resubmit and restart it. Some jobs may pick up where they left, but not everyone. Do not hog resources, as I mentioned. Take up everything just because they are there. Many programs write a lot of temp files, so always monitor them, remove them. If your program is finished, remove all the temp files. Monitor jobs periodically that they are running, that are not going into zombie state. Do monitor your disk usage. It's always crucial that you have enough space to write your output. If you don't have enough space to write your output and you submitted a job, the job is going to fail because you cannot write the output. You don't have enough space. Clean your temporary space and files and be considerate to other users. And this was the last slide. Okay, this slide actually tells how to transfer data between local machine and Xanadu cluster, or from Xanadu cluster to local machine. So in case of host, what you're trying to provide is a host transfer node. So in our case, we are going to specify transfer node. So which is sftp://transfer.cam.ucsc.edu. That's going to go in the place of host. You provide your user ID and you provide your password. And this is for our cluster. For your cluster, this address is going to change. Your user ID is going to change. Your password is going to change. Make sure you're using the host which is meant to be used for data transfer. Before you connect it, you will see that left side is populated. This is basically a file and folder from your local machine. Once you say quick connect, the right side gets populated. You will see files and folders here, which on the right panel. And then those are the files and folders from your cluster. And once you want, whichever file and folder you want to transfer, you simply click, select, and drag and drop on the other side. So if you want to do bring from the cluster, select on the left and select on the right and drop it on the right left, and it will bring it to local machine. If you are moving from local machine to the cluster, select on the left side and drag and drop on the right, and the files will start transferring. If there is if the files are too big, it may sometimes fail, but the good part about it is at bottom, it will tell you which are the failed transfers, and you can restart those transfers. So that's pretty good about that. I am pretty much done here, and there are 5 more minutes left, and I'm happy to take any questions. Otherwise, we are done for today. Hopefully, wasn't too much for today. But I would recommend to go through this material possibly to get a good hang of it.